ಏನ್ ಟ್ರೈನಿಂಗ್ ಸರ್ ಅದು ಬೇಸಿಕಲಿ?
The teachers training sir namda 2009 batch ಆಗಿದ್ದ government college teachers.
Oh, very good sir.
We give 21 day training ಕೊಡ್ತೀವಿ ಸರ್ ನಾವು teachers ಗೆ. ಅದರಲ್ಲಿ 3 aspects we focus on. One is teaching learning, second is research, and the third is student empowerment.
All these are very useful for NAC purpose and
yes
and overall development.
Sir, NAC they are useful for children, for students. NAC is a side business. It's not the main thing.
Of course, basically the primary receivers are the students.
Correct. ನಾವು ಮಾಡೋದು ಅವ್ರಿಗೆ ಅಲ್ವಾ, ಅದ್ NAC ಹೆಂಗ್ ನೋಡ್ಕೊಂತಾರ ಅವ್ರು ನೋಡ್ಕೊಳ್ಳಿ, ಬಟ್ ನಾವು ಮಾಡೋದು ಮಕ್ಕಳಿಗೆ. YouTube ಲೈವ್ ಆಯ್ತು ಅದು ಕಾಣ್ತಿದೆ. ಹಲೋ ಕೇಳ್ತಾ ಇದೆಯಾ ಸರ್? ಇದು ಯೂಟ್ಯೂಬ್ ಲೈವ್ ಅಲ್ಲಿ ಇದೆಯಾ? ಯೂಟ್ಯೂಬ್ ಲೈವ್ ಅಲ್ಲಿ ಇದೆಯಾ? ಅದ್ರ ಲಿಂಕ್ ಸಿಗುತ್ತಾ ಸರ್?
ಕಳ್ಸ್ಕೊಡ್ತೀವಿ ಸರ್.
ಅಲ್ಲಿ ಹಾಕ್ತೀನಿ ನೋಡಿ. ಅಲ್ಲಿ ಏನ್ ಕಾಣ್ತಿದೆ? ಅಲ್ಲಿ ಇಲ್ಲಿ ಏನ್ ಕಾಣ್ತಿದೆ?
ಸರ್ಗೆ
ಹಾಂ ಸರ್ ಕೆಂಗಣ್ಣ ಸ್ವಾಮಿ ಸರ್, ನಿಮ್ಮ ಹತ್ರ ಲಿಂಕ್ ಇದೆಯಲ್ಲ, ಅದು ಫಾರ್ವರ್ಡ್ ಮಾಡಿ ಸರ್ ಒಂಚೂರು ಅವ್ರಿಗೆ, ಶಿವಪ್ರಸಾದ್ ಸರ್.
ಕೆಂಗಣ್ಣ ಸ್ವಾಮಿ
ಆಮೇಲೆ ಮಾಡಿ, ಏನ್ ತೊಂದರೆ ಇಲ್ಲ. ಯು ಕ್ಯಾನ್ ಡೂ ಇಟ್ ಲೇಟರ್ ಆಲ್ಸೋ, ನೋ ಪ್ರಾಬ್ಲಮ್.
ಓಕೆ ಸರ್. Sir, we'll start at 10:30 ಅಲ್ಲ ಸರ್ ಎಕ್ಸಾಕ್ಟ್ಲಿ?
Yeah. Now it's how much? 10:29 now.
Yes sir.
ಒಂದ್ 3-4 ಜನನಾರು ಕೇಳೋರು ಇದಾರ?
ಸರ್
ಯಾಕೋ ನಿಮ್ದು ಸಿಗ್ನಲ್ ಬರ್ತಾ ಇಲ್ಲ ಸರ್.
ಸ್ವಲ್ಪ ನೆಟ್ವರ್ಕ್ ವೀಕ್ ಇದೆ ಅಲ್ಲಿ.
ಹೌದಾ? ಓಕೆ.
ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಶಿವಪ್ರಸಾದ್, ನಮಸ್ಕಾರ.
ಹೇಳು ಮಗನ್ ಸರ್, ನಮಸ್ಕಾರ. ಹೆಂಗದಿರಿ? Seeing you after long time.
Sound. Not able to hear.
Hello.
You're not able to hear, sir?
Can you hear me? Midun sir, am I audible?
Yes sir, good morning. You are audible.
Good morning. Thank you very much. The handsome Yelmagad sir is come.
Sir,
I don't know, there's some problem. I'm not able to hear.
Okay. It's okay, sir. Maybe you should go out and join again, sir. Rejoin.
Administrators, can you kindly look into the matter? I'm not able to hear.
sir, ಅವ್ರಿಗೆ ಟೆಕ್ನಿಕಲ್ ಪ್ರಾಬ್ಲಮ್ ಇದೆ ಅಂತ ದಿಕ್ಸೂಚಿ ಅವ್ರಿಗೆ ಹೇಳ್ಕೊಂಡು ಬನ್ನಿ.
ಸರ್ ಐ ಆಮ್ ಲುಕಿಂಗ್ ಅಟ್ ಇಟ್ ಸರ್. ಐ ಆಮ್ ರೆಸ್ಪಾಂಡಿಂಗ್ ಟು ಹಿಮ್.
ಓಕೆ.
ಅದಕ್ಕೆ ಅವ್ರು ಚಾಟ್ ಮಾಡ್ತಿದ್ದೀನಿ. ನಾನು ಕಾಲ್ ಮಾಡ್ತೀನಿ ಸರ್ ನಾನೀಗ.
ಇಲ್ಲಿ ಇಡಿ ನೆಟ್ ಗೊತ್ತಾಯ್ತಾ? ಯೂಟ್ಯೂಬ್ ಲಿಂಕ್ ಹಾಕಿದ್ದೆ ಅಂತ ಯೂಟ್ಯೂಬ್ ಚೆಕ್ ಮಾಡಿ. ಬಂದಿದೆ ಸರ್. Shall we start, sir?
I am ready.
Okay. Is there any problem to any other dignitaries present here? Audibility problem? Diksoochi, kindly look into the matter.
Sir, I will look into it, sir. Sorry, sir. Sir, principal sir, I will look into it, sir. ನಾನು ಅವ್ರ ಕಾಂಟ್ಯಾಕ್ಟ್ ಮಾಡ್ತೀನಿ ಸರ್, ಈಗ ಫೋನ್ ಮಾಡ್ತೀನಿ. Shall we start or like ಅದನ್ನ ಕ್ಲಿಯರ್ ಮಾಡಿ ಆಮೇಲೆ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ ಸರ್?
ನೀವೆಲ್ಲ ಕೆಮಿಸ್ಟ್ರಿ ಲ್ಯಾಬಲ್ಲಿ ಅಸೆಂಬಲ್ ಹಾಕಿ ಅಲ್ಲಿಂದ ಲಿಂಕ್ ಬರುತ್ತೆ, ಯೂಟ್ಯೂಬ್ ಲಿಂಕು ಜಾಯಿನ್ ಆಗಿ
Good morning, everyone. At the outset, I offer my respectful salutations to Guru Parampara of Sri Suttur Mutt and also seek the blessings of present Pontiff, His Holiness Jagadguru, Sri Shivaratri Desi Kendra Mahaswamiji. We are meeting to an online platform for a webinar on advances in material science. It gives me an immense pleasure to share the objective of the webinar with all the participants. Since humans have existed, we sought for better materials, and the materials available to the society have defined the very substance of civilization. The early blacksmiths, craftspeople, metallurgists who have paved the road for modern technology were considered the first material scientists. The different types of materials we use today, including metals, ceramics, polymers, composites, and semiconductors, all exist due to this advance in the field of material science. For manufacturers to make more sophisticated products, new materials are required. The process of creating new materials has always been laborious and slow. Researchers frequently had to test hundreds and even thousands of different materials one at a time in order to uncover the properties they are looking for. Scientists are accelerating invention at breakneck speed using potent modeling tools and advanced machine learning algorithms. The rapid development of the materials will have a significant effect during the following decade. One of the areas in material science that has gained a lot of popularity in recent years is nanotechnology. As Richard Feynman famously said during the annual meeting of the American Physical Society at Caltech, there is plenty of room at the bottom. The talk is widely regarded today as the original inspiration for the origin of nanoscience and nanotechnology. The developments in the nanotechnology provide a unique opportunity not only to develop new classes of materials, but also to do so in harmony with goal of sustainable development. Nanocomposites are one such example of cutting-edge nanomaterials. The mechanical, electrical, thermal, optical, electrochemical, catalytic qualities of these materials, which differ noticeably from those of the bulk components, make them of great interest. These potentially groundbreaking materials will be highly sought after and incredibly lucrative in a variety of industries, from very tiny manufacturing facilities to a large ones, that significantly benefit people and the environment by bringing new technologies and better economic opportunities to several industrial sectors, including automotive, construction, electronics, electrical, food packaging, and knowledge transfer. This webinar will showcase current advancement in the field of nanocomposites with an emphasis on multidisciplinary material science research. The purpose of this webinar is to promote better communication between and among the academic experts. Here today, we have with us eminent resource persons in the field of material science, namely Professor S.M. Shiva Prasad from Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, Dr. Channabasweshwar Yelmagar, scientist from Center for Nano and Soft Matter, Bangalore, and Dr. Mithun Dominic C.D., Assistant Professor, Sacred Heart College, Kochi. Let us get enlightened about nanomaterials and derive maximum benefit from this golden opportunity. I welcome all the participants to this webinar. Thank you one and all. Over to you, Ullas.
So, good. Ullas.
Yes, sir, you can start, sir.
Okay. Good morning to all present in this webinar. At the outset, I offer my humble pronouncements to the Lingaika Jagadguru Dr. Sri Shivaratri De Rajendra Swamiji, the founder president of JSS Mahavidyapita. My pronouns to the present pontiff and the president of JSS Mahavidyapita, Jagadguru from Sri Shivaratri Deshikendra Mahaswamiji. Today, the science departments and IQAC of JSS College of Arts, Commerce and Science, Nanjangud, have organized a webinar on the advances in material science, which has vast scope and varied dimensions. It is my privilege to welcome Professor S.M. Superhal, the Director of Higher Education Academy and a professor at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, a prestigious research institute in the country, and who is with us to deliver the keynote address on the webinar. Professor S.M. Shivaprasad, a renowned professor and a scientist who has several credits to his achievements. Sir did his PhD in thin film physics from Karnataka University, Dharwad, and postdoctoral research at IIT Delhi and University Sussex, UK. He is also the recipient of Doctor of Science from BSK University, Bellary. Before joining Jawaharlal Nehru Center for Advanced Scientific Research, he served for 2 decades at National Physical Laboratory, New Delhi. He is a visiting scientist at National Institute of Standards and Technology and in Rutgers University, USA, Tohoku University, Japan, and University of Ulm in Germany. His research interests are thin film surfaces and interfaces of material, as well as the growth and properties. He has published 296 research articles in the International Journal and 28 articles in National Journal, besides authoring 2 books and editing 1. He is the recipient of Young Scientist Award from the President of India, Raja Ramanna Award from the Government of Karnataka. He has been awarded with the Medal Lecture, Superconductivity and Material Science Awards, and Distinguished Lectureship Medal by the Material Research Society of India. He is the Indian representative to the International Union for Accounts Science Technology Applications, World Materials Research Institutions Forum, Europe-India Cooperation for Nanotechnology, Indo-Brazil Cooperation for Science. He is the Vice President of the Material Research Society of India. He is in the advisory board of BEL for night vision device development and for DRDO and for smart materials research. He is a member of the board of management of SDM Medical University and a visiting professor at KLE Technical University, Hubballi. He has a passion for cricket. As an accomplished cricket player, he played for his county and DDCA leagues. He represented his schools, colleges, and university in both cricket and tables. I feel very honored and privileged to extend a warm welcome to this national webinar for delivering keynote address, sir.
Thank you very much, sir. Thank you for your kind words. Yeah.
And another dignitary here, Professor, none other than very young and renowned Professor N.K. Lokanath, sir. He did his post graduation and as well PhD from the university. Later on, he joined Mysuru University as physics professor. Currently, he is the Director, Planning, Monitoring, Evaluation Board in the University of Mysuru. Earlier, he served as the Director of CDC College Development Council and as well the Coordinator of CPEPA in the same university. Professor Lokanath has many awards, has received many awards like Young Scientist Award and also the award from the 360 India. And apart from this, he has got his postdoctoral thesis from Samsung Biomedical Research Institute, Siwan in South Korea. As a scientist in Recon, Japan, he has also visited the University of Sangwon in South Korea. He has published over 465 research articles, both in national and international journals, and with a high H index of 27 and 3019 citations, overall citations. He has authored a chapter in the book on physics and also has 2 patents to his credit. He is also a recipient of a faculty research award by Career 360 India, and he is a member of various academic bodies, both national and international level. And he is here with us to deliver presidential address, and I welcome you, sir, wholeheartedly to this webinar. Thank you, sir. And the other dignitaries present here, they will be pursuing after this inaugural session, the resource person from Channabaseswara, Yamangad, and Mithun Dominic. And we will be having a welcome to them separately later on in the section. Anyhow, they are present here. I am extending a warm welcome to both of you, sir. And I welcome the key resource persons, academicians, research scholars, and other participants in this webinar. I personally welcome all the HODs of our college, science departments, IQAC coordinator, and other staff members of the college. And I welcome one and all present here for the webinar. Thank you very much, sir.
Thank you, sir. Yes, sir. Thank you, sir. So I humbly request Professor S.M. Shivaprasad, sir, to present his keynote address. Sir, over to you, sir.
Okay. Ellargu namaskara. I'm delighted to be in this program, though virtually, because now I start with paying my deepest and most sincere pranamas to the Guru Parampara of the Suttur Matha, because I'm one of the almost direct beneficiaries of the Suttur Matha, because my father studies as a poor student, poor boys in the poor boys hostel in the Suttur Matha. So our connections with the Matha, right from the previous and the present Swamijis, and we continue to get the blessings from them. Thank you for inviting me for this program. I'm delighted that a lot of my friends are here, Loknath sir, Elamagad sir, and Mithun. Yeah, very nice to see all of you. And nice to have new friends like Kendaganna Swami sir, the principal, and Sridevi madam so start making new friends from today. Okay, and also several of them. First of all, my request whenever I give a webinar is to request all of you to keep your videos on. See, it's very difficult to talk when I don't see the people on the other side. The beautiful smile and the beautiful eyes are necessary for a teacher, right? So without that, it's very, very difficult. So I request all of you to kindly keep your videos on. See, now I see the beautiful smile of Sridevi madam. Okay, Loknath sir. And of course, somebody else along joined, and then Midun is still not yet smiling. Okay, I want to see a smile from Midun. Yeah, very nice. And then UPK official, what's your name? Yeah.
So my name is Ullas, sir.
Ullas, okay. Ullas Dinda Iruvuru. Okay, right. Very nice, all of you. Nice to have you. Ravi Teja, can I also request you to switch on your video, please? Okay, if possible. Yeah, thank you all very much. And it's a wonderful thing because materials are changing quite a bit. So I'll probably start presenting my PPT, right? So before, yeah, okay, let me start sharing my PPT. Can you all see my PPT?
Yes, sir.
Yes, sir.
Okay. I've titled this topic as materials, the new convergence. Like Sridevi Madam mentioned, the way people were making materials in the past was with a lot of trial and errors. And now with machine learning and everything, you can do so many things before you actually make a material. But what I'll probably focus today is on something. Okay, yeah, maybe I request all of you to at least keep your videos on and keep your audios muted, because there is some disturbance which is coming from one side. So please keep your audios muted unless you want to talk to me. It will be very nice. Okay. Yeah. Okay. Thanks. Now it's clear. Thank you very much. So the topic I've chosen is the materials, the new convergence. So what I mean by new convergence is individually, like Sridevi Madam said, individually properties were looked by different directions, and one material had been assigned a certain property, a certain list of properties, and continued to be used that way. And they were only optimizing those parameters to make the material more useful. But now I think the modern material science has changed quite a bit. There's a convergence of materials. You can use a lot of composites. Not only that, you can make one material into different kinds of materials. And that is something I would like to share, because that is the modern trend in technology and in science and technology. I'd like to speak a little bit on that. So now, in research, the different kinds of materials we see, as mentioned by Madam, was nanomaterials, biomaterials, electronic materials, optical materials, magnetic materials, and computational science and theory, which is again used for the research of these materials. Okay, it's become completely an integral part of materials research is the computational science. Okay, I'll briefly go through this and then start talking about some of these interesting materials. So now, in terms of materials, you have ceramics and glasses, composites, polymers, metals and alloys, and semiconductors, right? These are the ones which are used as materials inside an industry, and where the strength of the material, the toughness, the ductility, and the physical properties were terribly, terribly important, and also sometimes electrical properties which are important. And these were defined very, very interestingly for a long time by their microstructure. So you just needed about 25x microscope to look at the microstructure and try to understand where the cracks are formed, where the deformations are formed, etc., where the defects are. That was enough for materials in the past. But now things have changed. So now actually material science is a beautiful field, because if you remember, the whole science earlier used to start with some science and then break up into specializations, like in doctors, right? So you have a dentist, then you have orthodontist, you have a pediatric dentist, so like the classification into different parts. But material science is again, which is converging all these sciences back together. So what it's doing is it's bringing what was called as earlier metallurgy, then what was called as ceramic studies, then what was called as solid state physics, and what was called as chemistry. It is putting them all together in study of materials and calling material science. So this is the first example of new academic discipline. This itself has emerged in this discipline by fusion rather than fission. Earlier studies were all breaking up into different parts, more specializations. Now you're bringing back all the specializations into one science, which is called as material science. And in this, I should remember the contribution of Professor C.N. Rao in making material science as a very dominant field is very, very large, and very important to realize his contribution to this field. So now you have now you study them as different materials, which is in addition to something like that with the biomaterials and nanomaterials, adding to the previously available electronic materials, optical materials, magnetic materials, etc. Okay, now let's go and see. Now, material science is also a part of art now. You see all these beautiful microscopic pictures, not only that, in the layers of materials, even at the macroscopic levels, have been used as an art. So it's a beautiful field in art itself of how materials, the beauty of the arrangement of different structures, micro and macro structures have been understood in terms of art. Okay, so earlier, the whole properties were built from the macro properties, right? When we remember Mendeleev, when he put together the first periodic table, he was looking at the reactivity, the activeness of a material, he started classifying them as different materials. But now it's become important to look from the quantum mechanics point of view. So now it's no longer just the macro properties, but we need to look at the periodic table in a quantum mechanics point of view, and let's see how we go about that a little bit later. Okay, so now you see here, now you have different kinds of materials, non-equilibrium materials, then soft materials, then the conventional materials, and then device systems, right? So all of them work together along with, okay, let me use a pointer here. Just one minute. Okay, right. So all this, the non-equilibrium materials, the soft materials, the conventional materials, the devices and systems groups work with the mathematical science group to form universal formulations. So that's what the fusion I was talking about. And you see here, this leads to a lot of new predictions. A non-equilibrium system, emergent dynamics. Okay, you must all be aware of this beautiful field called emergent dynamics. The networks of functions and topology. Okay, these are, I think, the new fields of research which are very intensely done. And a lot of these properties are predicted by these kind of calculations and measurements. And that makes the field very, very interesting. Now, this has also led to a very, very powerful system, especially called as green materials, especially in terms of application to energy. Because one way is energy harvesting. How do we produce energy? And the other way is how do we save energy? And then how do you make green materials for the cleaning up of the environment? Right? The pollution of the environment needs to be cleaned up. So how do you do this? This is another big emerging field in the field of materials. So let's look at the basic science a little bit. We all know that when two atoms are brought together from very far away, okay, when the internuclear distances are very large, then there is a small negative potential. But as you come very closer, then they form the attractive interactions, bring them to a very optimal condition when the bond is formed. So when I look at the energy, so the bonding probability becomes increased. But if I try to bring them closer, there is a repulsion because of the two interactions of the two electron systems, right? So we need optimal. So obviously you have bonding probabilities, then we also have anti-bonding properties, depending on where the electron is. If the electron is there present in between the bonds, then you have bonding properties. And if it is somewhere else, not between the atoms, then you get the anti-bonding properties, which makes materials very challenging. And not only that, it makes them very diverse. As I'll show you here, so this is what we have solved for hydrogen atom, for example. You know the shape of the orbital is spherical in terms of the s electrons. Then for the p electrons, you have these dumbbell-shaped things. Then more complicated is the d electrons, and then for the f electrons, right? So now you see when the distribution of the electrons are not just spherical, so they have a certain shape. And this shape determines how they bond with other atoms, right? Because it depends on the shape. If the shape is in this direction, then the bonding probability in this direction becomes more. If there is no electron probability in this direction, then the bonding becomes weak. This leads to what are called as different kinds of bonds, right? We get the cubic bond, the body-centered bond, the face-centered cubic bonds. I mean, different kinds of shapes are coming because of the shapes of these orbitals. And very interestingly, complex the shapes of these orbitals are not studied for other atoms, very complicated, but hopefully in future ML and AI will bring them also into feasible control. So we'll be able to do some more studies of this as in coming times, I think, which will take the front seat in kind of research which is being done. So now, okay, so here, so you see here, when these bonds, the same curve which was plotted, now for s electrons and p electrons, if there is an overlap of the s and p electrons, then there is a hybridization, right? So very interestingly, then the bonds become very different, especially, for example, the best example has been graphite, okay, I mean the carbon atoms in one layer, which has got the sp bond, which is called as commonly called as graphene now, for example, is a hot topic. When you have orientation of the hybrid orbitals are linear in nature. But then you could also have two p bonds overlapping the S bond, then you have what is called as sp2 hybridization. Then you see here the structure is very different, and with the bond taking, it becomes a triangular planar structure, right? Which we all know very well. And if you have three p orbitals bonding, then you have the tetrahedral structure which comes out of it. So beautiful, the organization of the electrons and the distribution of the probability determines what kind of bonding and what kind of structure it is. I think that fundamental understanding is very essential to really appreciate okay, how the materials are made, or in the future, how to tailor make materials, which are very important in the way the properties we want. Right. So now I look at the electronic band structure of graphene, and see, it makes it very interesting. You know that it has a very sharp Dirac cone here, and which gives an infinite mobility, almost an infinite mobility for the graphene. And then, of course, now we are also trying to make silicene and germane, which are also similar with those kind of properties like the graphene. So these are also interesting fields for research in the coming times. And then, of course, doping them becomes very interesting. You see here, this is my delta function, and then you have this doping. When you do n-type, p-type of doping, then pristine material has a Fermi level in the middle of it, etc. These are something, I'll just glance through it. I don't want to go into the details, but just tell you how people are thinking about materials. And that is how you start seeing fields like metallurgy departments have been closing down in engineering departments. Okay, it's all being called as material science. Similarly, solid state physics has been closed down now. It is also being called material science. So this convergence of different fields of chemistry and physics and engineering, everything coming together is making materials a very, very exciting prospect for the future. Okay, so so let me jump this, and so we have now very interesting materials called as 2D materials, right? 2D materials, which are different kinds of hybridization, especially the sp hybridization. So you have several materials: tungsten oxide, molybdenum oxide. I mean, all sorts of tungsten selenide, molybdenum selenide, boron nitride. These are being very extensively studied in terms of 2D properties of these materials. And then you have, and these 2D properties show metallic behavior, semiconductor behavior, and also insulating behavior. So you start putting them in different layers, you start getting different properties. So the idea that one material has one property is no longer valid, right? So it depends on how you are able to put the materials together. Engineer the materials will give us what kind of properties they want. So that gives us a flexibility of making the properties we desire. So what we call as tailor making of properties, one particular material. So now see, this 2D layers, for example, is used for clay and drug delivery. You can make these beautiful layers of materials, layered silicates, for example, and then put them into polymers. So you have layered silicates inside the polymer. So this, and in between these, you can intercalate drug molecules. So you can push this, then you can do an intercalation so that it get mixed up. And so the control of this intercalation decides the release of the drug molecule. So then you can do exfoliation. So you can release the drug molecules whenever desired, depending on the property. Say, for example, the pH or the temperature or some other property. So you see, what is very interesting in this material is, so now this material is a complex material, which you cannot call just as a silicate material, right? It has many materials combined together, which are called as composites, which are again have been the workhorse for quite some time now, for a couple of decades now, working on these kind of polymers. It's a beautiful method of drug delivery, which will probably solve many of these problems of the allopathic medicine, the side effects and the cost and other issues, and then deliver the medicine at the targeted medicine, which will make it very useful. Okay, then we have very interesting materials called as metal organic frameworks. This is a combination of organic and metals. So this gives us rigidity because of metals and the flexibility due to the organic materials. And these are becoming very powerful storage materials. They're not only storage, but also for energy production. But these are being considered very seriously for batteries and supercapacitors. And we know the challenge for batteries, especially with the electrical vehicles becoming the norm, we are going to have a lot of research in battery research. And now we all know that water splitting and battery research have become the most important fields of research everywhere, all over the world. And we need to get high energy density of batteries and also high power densities of batteries. And that is where the challenge is right. We are also glad to know that we all saw in the newspaper in the last couple of days that a lot of lithium deposits have been found in Jammu and Kashmir. And very high quality and easily reducible material has been built. So that's a very good news for India's battery future in the coming times. This appeared only day before yesterday, that the lithium storage has been found in huge quantities in Jammu and Kashmir. Right. Very good. Let's go ahead. And then we have something called as even more interesting, which is called as supramolecules. So like you put atoms together and which form covalent bonds and you call them as molecules. But now you can put these clusters of molecules themselves and treat them as atoms. Okay. And then call the whole molecule of the clusters of atoms as called as supramolecules. So what are atoms for a molecule? Here molecules are for the supramolecules. And what are covalent bond? Now you have a intermolecular bonds. So these obviously are weaker bonds, but this is how biology works. So all our biology systems, like for example the DNA or anything of that sort, they work on this basis. Now it's very interesting that these also have electrical properties. So having electrical properties as well as these supra assemblies, okay, can make this material a very powerful material in studying the future, especially related to the biological systems. And integrating biological systems with the non-biological systems will be some of the future which is going to happen in the coming days. And now we have transition metal oxides. Of course, they have been extensively studied in the ABO3 structure, which are called as perovskites, for example. Then you have atoms sitting in different positions, and these give you very interesting properties such as ferroelectricity, magnetic properties, and multiferroic properties. And then a combination which basically depends on the spin and the charge of these materials. So how do we exchange the spin and the charge of the materials so that we can get these kind of properties? And these will see a lot of applications, especially now we see a lot of applications of perovskites in solar cells, but it can happen because of these strain fields can be controlled, magnetic restriction can be there, magnetic field, magnetoelectricity, ferroelectricity, electric fields, piezoelectricity, ferroelectricity makes these a very diverse kind of material which can be used for. I can also do aluminum gallium nitride, aluminum gallium phosphide arsenide. I can go on mixing 2 to 3 different proportions, and each time I have a material, I can actually start forming different semiconductors, which actually means different band gaps and different semiconductors. So I can like this create an infinite number of semiconductors, and then I can tune them to the band gap I require. So this is one way of changing the band gap of the material is by alloying elements. So this can be done. These are called as 3-5 compounds. And similarly, I can do 2 and 6 compounds. I can use 2 6 compounds. Also do because 2 and 6 8 divided by 2 is 4. So I get 4 electrons in the outer. So this is what how you can form many semiconductors, 3-5 semiconductors, the naturally available silicon and germanium. Along with that, now we have infinite number of band-made semiconductors, and that gives you different colors, different radiations you can get out of the images. Because you remember, I started this by telling this is necessary because I have to make a 1553 nanometer semiconductor, because if I want to get a radiation for fiber optic cables. So now let us look at the indirect band gap. So you see the indirect band gap here in the E which is A diagram. You see, if you go from here to the lowest energy in the road for the electrons, it is not direct in the sense that you need to change the momentum also. If you need to change the momentum, then it is very difficult. And this is not the lowest. So this is the lowest energy. So the electrons wants to go here, but it can't sit there. So let's see what happens to this electron. So now I shine with light, for example. I can kick it in any way. I can do it by putting electricity. I can put it by putting light. I can do it by mechanically rubbing, so, or thermal heating or something. Somewhere I have to give it enough energy for it to go. Right now I'm showing a picture when a sunlight is put onto this semiconductor. This semiconductor again gets the energy, gets kicked up to the roads, from its house to the road. But this, because it's now here, it is difficult for it to come here until it also changes its momentum. That means to change its momentum, it needs somebody else's help. It cannot do on its own. So it needs phonons. That means the vibrations of atoms, right? Those energies should bring them. So using them is so difficult that the electron finds it difficult to come back. So it continues to stay in the road itself. So let's see this electron, what happens here. It continues to stay in the road itself. You see here, and travels in the road when I put a bias on them. So that means I start getting electrons in an indirect band gap semiconductor to stay in the in its conduction band. So this helps. That means the lifetime of the electrons in the conduction band is so much higher that the probability of it being drawn out without reduces the recombination probability by a very large amount. And that I think is terribly important to distinguish between materials where you can make a LED or a solar cell. I'll tell you this as I go along. So now, but you need to make an LED out of it, because you got just a semiconductor won't work. Okay, as you can see, a semiconductor don't work. You need a LED, because in an LED you have a P region, lot of holes, and in an N region which has lot of electrons. So when I make an LED and I put a proper bias on them, a forward bias, the holes move from one side to the other, and the electron moves from the opposite side. And when they come and reach and meet each other, they get married. And when they get married, the electron and the hole recombine, and the energy difference of them gives us light, right? Which I showed earlier. But now it's not single semiconductor, but two semiconductor, means the same semiconductor maybe with two different dopants which are connecting. So this LED formation is like a marriage, right? The electron and holes getting married, and like you produce children in a marriage, you start producing light here. But now let's see the other way around. Now, if I use a indirect band gap semiconductor, then I make p-type and n-type region. That means the electron and holes were comfortably sitting together. I put a bias, I separate them and make them travel in opposite sides. So this is similar to a diverse case. So the LED is a marriage case, and the solar cell is a diverse case, right? So, but both are important. Sometimes both of them work very well. Only thing you can see here is the marriage produces light, and here the marriage produces current. So, which means sometimes you can use the current for light, but basically you'll face the current. Okay. So, but the solution is, but this also means that there's only one band gap, and it absorbs only certain part of the wavelength. Say, for example, this is the solar energy spectrum. We all know the solar energy spectrum has huge range from ultraviolet to infrared, while through the visible range. So you have silicon with a band gap of 1.1 electron volt absorbs only certain part of the radiation. It doesn't absorb all the radiation. So what you need to do is to use something called as a multiple band gap heterostructures, which means that you need different semiconductors with different band gaps, pack them together. And when you pack them together, different part, say for example, this part will absorb this part, this will do this part, this will do this part, this will do this part, and this will do this part. So like that, you can get all the absorption of all the light which comes from the sun. So you can get a super efficient solar cell, right? So these are called as tandem heterostructures or multi-band gaps structures. So similarly, if you want to get white light, okay, the best way to get a white LED is to have such structures. Then you get different colors, red, green, and blue mixing together in the right combination gives you the perfect white light. But as you know, the LEDs right now, the white LEDs we know are not perfect white lights, because they are made in a different way. They are not made this way, but they are made with blue LEDs, which go and have yellow phosphors on them. And that's why they interact with the phosphors and give us the white light. If you look back at your mobile phone, say for example, or any LED in your mobile phone flash, for example, you will see the yellow color coating there, which is basically yellow phosphors which are coated to interact with the blue light. Okay, so now, as I said, one semiconductor can do the job of an LED, but it is not enough. So I need a PN junction. So because I have a lot of electrons and lot of holes, and the probability of recombination becomes very high, so I use an LED. But again, this is not enough. To get a real efficient LED, I need to make semiconductor double heterostructures, which is basically you bake a small band gap material sandwiched between two large gap materials, and you bias in such a way that the electrons which are produced in this, by exciting this semiconductor, the electrons can come and fall into this well. And this size of this well is a quantum well. That means we know particle in a box. So similarly, when the well size becomes very small, the energy levels go higher and higher, and the energy level and the electrons go at higher energies, right? So we also know that when there is a infinite particle in a box with infinite potentials, the electrons are excited and remain inside. But once we have a finite potential, then there's a probability of electrons to come out of the materials, which we call it as effervescence, or also called as tunneling of electrons. So I can have two such materials next to each other so that the electron can tunnel from one box to the other, which is quantum mechanical tunneling. So coming back to this is something the semiconductor double heterostructure was again was a very important discovery. Alfa Rao and Comer got the Nobel Prize in year 2000 for making this heterostructure, after which LEDs have become very, very powerful. But still, the efficiencies are very low. They are only of about 22, 24 lumens per watt. but the capacity of LEDs for each color is about nearly 150 lumens per watt. So this is still a lot of interest on going on this material, which excited us to get into this material. Okay. Anyway, coming back to this one. Let me see why it's not changing. Okay. So now look, I want to bring another dimension, which is the nanomaterial dimension. So this was the semiconductor dimension, the simple semiconductor we knew for a long time, but the interesting heterostructures which are reasonably new. So now let me bring the new semiconductor, I mean the new science, which is like Madam said, it is the new science of the nanoscience. So what's nanoscience? I call it as a modern alchemy. You know, alchemists who wanted to try everything material into gold, convert one material into another, it was not possible, but they found out some fantastic chemistry in the whole process. But at the same time, with nanomaterials, this becomes possible. I can make one material behave like another material, and that is the beauty. So how does it work? So now, oops, what happened? Sorry, not work. Okay, so now let's take an atom here, for example, a small atom with 2 electrons. So that means there's a house of electrons with this energy and the roads for electron, which is 2 energy. So these are occupied and these are unoccupied states. Now I put another atom, that means there are 4 electrons and you need roads for 4 electrons. And because of the Pauli's exclusion principle, we need to create more states. All electrons cannot travel in the same state, so we need to create more states. So like that, when I go on adding atoms, I have to go on increasing the size of my house and also go on increasing the size of my roads on which these electrons travel. And this I can go on increasing until I attain a saturation, which is basically the Avogadro's number. So when I reach the Avogadro's number, it gets saturated. Say, for example, in this particular case, there's a band gap has been created. But of course, if these states were different, there could have been an overlap of band gaps and I've created a metal. But here I'm creating a semiconductor. And or if it's very far away, I could have created an insulator depending on these energy levels, right? So you see here, what we studied earlier was called as atomic physics and molecular physics in this region. And then we studied here in the bulk material, which we called as solid state physics or condensed matter physics for a long time. But what was ignored for a long time was the nanoscience in between. So what happens when the sizes were smaller than the density of these atoms were lesser than the Avogadro's number? What happens to the properties of these materials? This has emerged as for the last maybe 2 or 3 decades. Of course, Madam mentioned about Richard Feynman's statement is the major motivating force. I do agree. But at the same time, we should remember Michael Faraday long ago had also made gold particles which are tiny, and he showed that they also had different properties. So the origin of actually making nanoparticles goes to Michael Faraday. But the concepts of Richard Feynman doing the experiments that we can explain these by using quantum mechanics gave a big boost to this research in this field. So now you see here, what is interesting is, for example, a semiconductor, the band gap determines the property of a semiconductor. So now I can take this semiconductor, make it smaller and smaller. I can make the band gap bigger. I make it even smaller. I can make it even bigger. Ultimately, it comes to the in the atomic configuration, right? So I can go on in between here and go on changing the band gap of the material. That means I can take the same material by just changing the size. I can produce band gap. For example, in cadmium selenide here, if I have 8 nanometer particles, then I can produce red color because the band gap is very small and the red color comes out of it. But then if I go on in between, I can create yellow color, I can create the green color, then I can create the blue colors by making 2 nanometer particles. It's one material, different properties. I think that is the beauty of why we call this as a modern alchemy, right? So now let's see what are the important properties of a nanomaterial. What happens? What are the different things with that? Obviously, when the nanomaterial becomes very small, the free electrons, for example, in metals, are restricted to a small region. We call this as electron confinement. Say, for example, in a 3D material, the electrons can have all different velocities, okay, or they can travel in different mobilities or energies. That means they can have different energy states. And when I plot them, it's parabolic, basically based on the equation E is equal to h cross square k square by 2m. So k square forms the parabolic. So when you have energy, the density of states are continuous parabolic in the nature. But now if I restrict this, make this 3D material into a 2D material, means I remove material and make it very thin layer, then obviously I don't have all the states available, because some states which were in this direction have been cut off. So instead of becoming like this curve forms, these steps go away. I mean, there are many energies which go away and form this kind of a step-like structure. This is in a 2D gas. Now, if I further go and make this into a thin line, for example, I mean, which I call as a nanowire, then more states which were supposed to like this, again, more states are removed. So you can see here low energy states, the high energy states can, the low energy states can remove, but the high energy states don't here. So this itself gets converted into this kind of a structure, right? You can see very clearly. And then if I go further and make it into one quantum dot, that means the electrons are restricted in all directions. It's almost like an atom. That means you are putting the electrons in specific places, in specific positions. And then that is how you can form specific states. The density of states are fixed. Of course, when you ultimately go to an atom, this will be a Dirac delta function. That means there will be only straight lines of the density of states. Right. So you see here, so electron confinement becomes a very, very important property for physicists, that we can actually control the house and the roads for electrons. And so once I control the house and roads for the electrons, I can make all the transitions controllable and according to my requirement. And then, of course, defects engineering, the engineers love this, that you can actually put in defects and remove defects very efficiently in nanomaterials. And defects are not defects, but they are very powerful. For example, doping. Doping is a defect phenomena, but it's very, very useful for semiconductors. So similarly, many, many defect properties can be controlled by having this. The surface itself is a defect. So when the material becomes very small, then the ratio of the number of surface atoms to the atoms inside becomes very large. That means every nanoparticle is mostly only a surface. That means these atoms, for example, don't have bonds on this side. They only have bonds on this side. So it's a defect. So similarly, most of the atoms in a nanomaterial become defects. So how you control them, how you form them, decides the kinetics of growth, what we call, and whether we have thermodynamically they come to an equilibrium, or they're kinetically, you can control them, how they grow, determine the properties of the materials. So not only the size, but also how you form the materials, the kinetics of growth also give you a control on the properties. So because the surface to volume ratio enormously increases, for example, here you see, because when I take, suppose I take 1 cube of sugar molecules, which has a 1 centimeter square, 6 faces, so 6 centimeters square. But if I break it into 1 nanometer particles, okay, tiny particles, each of them has 6 nanometer square surface area. But if I add the number of particles I can make out of that 1 centimeter, you will calculate and see it is much larger than a cricket ground. That actually means that you can play cricket in a test tube. And that is the beauty of why chemists love it, because they can do a lot of chemical reactions in a small region, because the surface phenomena, say, for example, catalysis or any light emission absorption phenomena, all sorts of interactions become enormously large because of the surface. Okay, surface to volume ratio enhances. Okay, but still, with all these major discoveries and understanding of the nanomaterials, we know nanomaterials very well now. We can understand it by using quantum mechanics. Quantum mechanics plays a major role in that means we are actually looking at the wave property of the material of the electrons. We understand so many things, but still the expected change in the whole world for major applications has not yet come because of the problem of the assembly. See, the problem is I can make a nanomaterial, okay, but ultimately if I want to make a bulk material, I want to make a pen out of it, I have to put all those nanomaterials together. When I put them together again, they lose their nanoproperties, right? Because the idea, because they are different only when they are separated as nanoparticles. But when I put them together again, they become bulk and they lose their property. So the challenge now in the future, which is going to be more of an engineering problem, is how do I make nanoparticles and put them together, but still they should not lose their nanoproperties. So what is the challenge? And that is what I think is the challenge for material science. I'm sure a lot of people are working on assembly. There are some major breakthroughs have happened, but still not yet to the engineering level. And that's why once the assembly can be taken up very seriously, amazing materials will actually emerge out of nanoscience in the coming times. So in nanosystems, the mechanical forces are very weak, gravitational forces are weak, viscosity surface becomes very important. They also change with the size and properties because of the surface area changing. And then molecular collisions is not average as just the pressure. So you cannot use the normal Boyle's law, the Charles law, looking at molecular collisions. The thermal transfer is easy because again the surface area is very large, and so thus the characteristic length scale is very important. So length scale in which your properties becomes very important to define what kind of properties are there in the material. So like this is example of gold. We all know this. Gold is the beautiful yellow. Then I can make it blue. I can make it red, orange, yellow, and colorless also by making tiny. This is the work which was initially done by Michael Faraday a long time ago. Not only it is about the size, but also we see shapes of materials. I can make them triangular. Say, for example, I make it wedge shape, like a triangular shape. Then different regions give me different sizes. That means different properties. So that means I can make a combination of properties and emerge out with new properties, which are different from the existing properties, which are called as emergent properties of these materials. So this is something again which can happen. So now we started thinking how to enhance the efficiency of these LEDs. So because we thought now it's important for me to combine the semiconductor properties of gallium nitride, for example, and the nano properties, the structures of these materials. So we thought, let's look at gallium nitride. Gallium nitride is a wide bandgap semiconductor. To make blue light, we need a very large bandgap. Red is very. That's why initially we used to see red LEDs, then green LEDs, yellow LEDs, etc. But we did not see blue LEDs for a long time. Blue LEDs are a relatively recent phenomena. And after the blue LEDs came, then we were able to make the white LEDs. So blue LEDs became a very, very critical. And you know that Shuji Nakamura obtained his Nobel Prize for making this the gallium nitride LEDs. But what is important here is the same structure. It's a direct bandgap material. That means the electron can go to the house, to the road very efficiently, and then also come back and recombine efficiently to give us good light. But the problem is when you're making these materials, you should not have any, if somebody is going from the house to the road, they should not have any canteen or pani puri or some distraction in between. If they have distraction in between, they will go there rather than go to the conduction band. This happens if there are defects in the material. So there will be defect states which are between the valence band and the conduction band. And if there are defect states, then the electrons which make a transition from here to here or here to here go to these states which may or may not give out light. Even if they give out light, then the radiation of the wavelength of this light will be different because the energy involved is much different. So the idea is, how do I enhance excitation energy? That means I want all the valence band electrons to go to the conduction band very efficiently without losing energy. Then also I want to enhance the recombination. Once it comes back, what is the probability of recombination, which becomes very high. And then also I want to eliminate defects so that there are no defect states in the middle. This was not enough. There was another challenge in these materials. Gallium nitride is a very large refractive index. Yeah, more than 3. That means all the light which is produced inside, most of it will get totally reflected, and there's a huge loss, reflection loss. The light doesn't come out. So this became a major problem with these materials. So that means we had a material problem, the purity of the material problem, and other was a geometric problem. Okay, how do I take this problem and this problem is the challenge, right? So that's why we started. Then in an MBE chamber, we wanted to grow material. One of the problems with gallium nitride is it doesn't have a native substrate. So in the sense that it doesn't have a native substrate, that means I have to grow it on some other substrate. Sapphire is a beautiful substrate. Now, of course, we are also working on silicon and other substrate. Even silicon carbide is a beautiful substrate, but very expensive and also not transparent. So we need a substrate which is transparent as well as matches with the lattice parameter. And that does not happen very well. So that's why whenever I grow gallium nitride on a sapphire substrate, there's a lattice mismatch of about 16%, which makes dislocations in the material. You know, you have two kinds of dislocations. If the lattices shift this way, we get edge dislocation. And if they change like this, we call it a screw dislocation. And these dislocations carry through the material and create a lot of defects. This has been one of the major limitations in the efficiency of the gallium nitride based LEDs. So we thought this can be sorted out if we can make nanomaterials of this wedge shaped structures. So we were struggling to find how to make these wedge shaped structures by kinetics, growth kinetics, not by lithography or anything, because lithography can create other problems. So, and the dimensions of the kind of dimensions we are talking about, we may not be able to reach. So how do we create these kind of dimensions, these kind of structures using just the kinetics of growth is something we kept on trying. With a lot of hard work, we were able to come to a structure like this. It was very interesting. This structure, you can see this looks very bad porous material, but it has been amazing. I'll show you how the convergence of semiconductors and nanomaterials have given rise to amazing properties which we never thought could have happened. Okay, this is that's why it kept us engaged for many, for nearly about 5 to 6, 7 years. It kept us engaged. Just this material. We stopped doing everything else and started looking at this material. Say, for example, see here, this is a gallium nitride film, which commercial use of a film. And this is what we have grown and make them different, right? We have grown all these kind of films here. Just to show you, so for example, the commercial material, which is used for LEDs right now, the efficiency of a photoluminescence is so small. But when I go on making it porous, okay, you see here the efficiency increases. Very interestingly, you know, this is nearly about 100 times larger efficiency in this material. Not only in terms of enhancement in the peak height, but also the width of the peak increases. This is typically very, very surprising, because once the width of the peak increases, usually there is a fall in the amount of intensity of the light which comes with these materials. But so we studied, looked at its high resolution microscope, tried to start seeing, then we saw that the defects were very less in these materials. So less, you can see here at the interface that the defects culminated very easily. And also because of the strain in these nanomaterials, the defects can go, because of the strain, they can go to the edge. And in the main material, there will be no defects in this material, so they can become very efficient. And also because of the angle. So what we tried to do is we tried to see, okay, what is the, we did some simulations, finite time domain calculations, to see what is the role of the refractive index and the purity of the material, or the defectless material of the material. How do we compare the two? So we could not do that experiment. Again, there's a simulation, which I'll avoid this simulation, but just show you the results of that. The result is that you see a flat film only on the based on the refractive index. There's a big change in this material from a flat film to the porous film. So that means I can get more light out of those wedges because of the shape of the films. So I can see that also plotted in terms of this graph. Okay, so then we put, so if we are telling, if you remember, I also talked about plasmons. So plasmons, if I can make nanoparticles of metals sitting on a surface, if I excite those electrons inside that material, the plasmonic energy in those materials gets stored in that in that nanoparticle. Now, if I give another radiation to that, they can couple together and form an enhanced radiation. Okay, so I think this coupling of the plasmonic energy with the band gaps release energy was something we wanted to try. So we put some silver nanoparticles on this. You can see these tiny circular spherical things we put on these materials and looked at. And lo and behold, there was a huge increase in signal. It's already increased from the commercial, I told you earlier, and now another, almost 100 times it increased. So nearly we were able to increase the signal from the commercial film to about 500 times by just making different nanostructures. So that I think was very important. So then we tried to understand it by putting this, what you see in this picture, these are gallium nitride nanoballs, and these are spherical balls are the silver nanoparticles. And the typical size of these silver nanoparticles is about 20 nanometers. So you see the edge of the wall is less than 5 nanometers. And this became very important. I'll show you as we go along. Interesting, then we try to model it, how the coupling of the band excitation with the plasmonic resonance will happen, so that a lot of light is released, which we're trying to model that. So now let's come to, we all know what is Raman effect. Okay, Raman, one of the greatest scientists India has produced, for his beautiful understanding of saying, because of the vibration of molecules, the incident beam energy either absorbs energy and loses energy or gains energy, which are called as the Stokes and the anti-Stokes. So you can see the reflection of the vibration in the light which has been emitted in this inelastic emission of light. Now, by putting silver nanoparticles on these surfaces, we can enhance the Raman signal by about a million times. This is called a surface enhanced Raman spectroscopy, and again, because of the plasmonic coupling. So I can create this plasmonic coupling and enhance the signal by about a million times. So by putting the silver particles on these materials, we tried to see how it happens, and also did some simulations to see where are the hotspots, how it is distributed, energy is distributed, etc. And then we found out that it is possible to see that. And when we do the experiment also, look, this is the normal Raman signal we can get from a material. Once I put silver nanoparticles, look at the beautiful signature it has. The fingerprinting becomes so much easier with these nanomaterials. So with this, we could detect up to 10 to the power of minus 10 molar of the of the material, and the lowest detectable concentration becomes about 10 to the power minus 10. So this becomes a very important material for detecting early diseases of materials. So this was just because of the coupling of the surface plasma in the nanoparticles. Now, as I told you, to put that 1553 nanometers laser, I need to create many lasers coupled to each other, and the light coming out of that in a very sharp way, so that I can put it into the fiber optics. So the lasers are made like this, a very complex structure. You see here multiple layers of different materials, whether reflectors, Bragg reflectors, okay, many active regions, substrate, so like that, many regions. So we thought we already have a material like this. Let's see how the light comes out of this. So we took this material, which looked like this from the top. It's a lot of pores, okay, which are just formed by kinetics. They're not drilled through or anything of that sort. So we wanted to look to see how light comes of this material. So we did what is called as cathodoluminescence. Cathodoluminescence is basically a photoluminescence by using electron beam. And electron beam, because it has no charge, can be focused into a very sharp beam. And like in an electron microscope, for example. In fact, the cathodoluminescence is done in a scanning electron microscope, a field emission scanning microscope. So I can actually find out where the light is coming out of the material. And amazingly, what we saw is that the light actually comes from the holes and not from the walls of these materials. Because you see, very interestingly, wall is the one where the light should come out. But we are seeing the lights from these holes, as you can see with the one-to-one correspondence of these signals. So that became very important. Then we started studying it very carefully. When I varied the beam energy, I started seeing something very interesting. One, I saw the bandage emission, but when I increase the energy of the electron beam, I see the bandage emission goes down, and another emission at about half the value, okay, or double the value in terms of lambda, goes on increasing. A broad peak starts emerging. And this is the picture of how the SEM picture or the cathodoluminescence map looks like. Okay, then this becomes very curious for us to understand why two wavelengths, and then why is one increasing and the other one decreasing. So ultimately, the number of photons are the same. So we plot this graph. You can see here, no, that's also not true. The ratio did not remain constant. Okay, so now we tried to again did some calculation, numerical solutions, solved some Schrodinger's coupled wave equations, and tried to understand how this actually happens. Very interestingly, we saw evidence for a spontaneous parametric down conversion. That means the photon of light which was traveling in this material, because this is a non-centrosymmetric material. That means it is not centrosymmetric in the sense that it has a built-in electric field inside that material, gallium nitride, because there is not equal distribution of gallium and nitrogen charges. So there is a built-in field inside that. So when I put this light creates, it actually breaks up that photon into two photons. And that is what we call a spontaneous parametric down conversion. So that's what was happening in this case. And we did that calculation, also showed that it is possible. And now, interestingly, the material, again, if the light travels longer in this material, it will again get reconverted into blue light. And that is why in the normal condition, we may not be able to see it. But now, by making these films cut in this particular angle, as you can see here, this angle, where it is red, already means made that conversion, it has made this conversion, I can get that light out of it. And that was the second peak I was seeing in my in our cathodoluminescence experiment. And that is, I think, very important and very interestingly. So we were getting, instead of the band emission which was in the ultraviolet, now we are getting a radiation in the infrared, which is very close to the 1553 nanometers, which I talked about. So now we did this same studies at low temperature, at the liquid nitrogen temperature. Very difficult experiment, but the cathodoluminescence at low temperature, but it gave us very interesting result. You see this, the conversion, of course, is taking place from this bandage emission to the infrared emission. But you see here, now the peak is much sharper. Okay, so like a laser-like emission. We are still not confident of calling it like a laser emission, but it is something like we call it as laser-like spontaneous emission, because it's not a stimulated emission like in a laser, right? So it is a spontaneous emission. So whether it's a laser or not, you don't know. It may be affected by something called as a Purcell effect, okay, which is matched in a resonant cavity. So these could be resonant cavities where the light couples resonance and creates this kind of a sharp beam. So we are still in the process of understanding it. So again, many studies, and so it shows also a threshold, which also shows that it is laser-like. So let's see. Let's see what happens. But if it is true, then that means we can produce the smallest lasers possible. Okay, that means we can produce even 20 nanometer lasers. which are not yet been able to do. I mean, anybody is not able to do. So we're working on that to try to understand what it is. But another interesting property, so these are all expected properties because of the band gap and because of the plasmonic resonance and the decoupling and the spontaneous conversion. But what was very interesting about these materials is one of my students just touched with the multimeter and he found this material very, very highly conducting, which is surprising. With a band gap of 3.4 electron volts showing photoluminescence of that value, it should not become conducting because there are no free electrons in these materials. So how they are conducting? Then it gives us a new dimension for this study. And we started studying why are these conducting, so well conducting. Okay, and so I collaborated with Subhabrata Dar from IIT Bombay, and we did. He is an expert in low temperature measurements, so we tried to understand what. So we did this in terms of making an FET out of that. Then we looked at the mobility, and the mobility of this material showed very large mobility, almost 20,000. Though for a 2D GAN film, gallium nitride, it should not be more than 300, around 300. But now we are seeing 20,000. So what is the cost for this? So that means I have a insulator-like material which gives me semiconductor-like light, plus it's also a conductor. The same material behaving in as an insulator, semiconductor, and metal was very, very surprising for us. So we did that, did some low temperature studies, and understood the phenomena that there is weak localization in these materials. And that means it is giving evidence for a 2D electron gas in this material. 2D electron gas is an amazing material. I mean, amazing system to study. And this also seems to show even at room temperature, which was a bit surprising. Okay, so we again did some calculations to understand what is actually happening in these materials and try to understand. And then we came out with the theory saying that because of the surface states of these materials, which have dangling bonds, actually those electrons get pushed inside, and you form a two-dimensional electron gas in the middle of these, in the middle of these wedges. And so these 2D electrons are protected from outside, right? Because outside shade. So we tried to saturate these dangling bonds by putting various gases on top of it, but we could not because these electrons have already been pushed inside. So this is something like what the topological insulators show. So topological insulators show also the surface states are protected. They are extremely high conducting with a high mobility. Okay, and so that means the surface states are protected. So whether we have something like that, we still don't know. We are still, if somebody is interested in these kind of, or you're doing this kind of work, interaction with you or a collaboration will be very useful to us. Okay, so now coming to this, then obviously there were free electrons, and that's why a two-dimensional electron gas was formed, because from the dangling bonds. Then obviously Professor Rao and Sundaresan had come out with many experiments to show some of the nanomaterials display ferroelectricity in these materials, even oxide materials, which are not expected to be magnetic because of the surface dangling bonds. So we also wanted to see if these materials show ferromagnetism. Yes, we did see ferromagnetism. And then we did some careful study to understand how it shows. And that ferromagnetism, you see, it shows a TC above room temperature. That means I can get a ferromagnetic material out of these materials, which is above room temperature, which is amazing. A two-dimensional electron gas above, amazing, right? Amazing material you can see here. So then we looked at where the ferromagnetism is coming from. Then we did some MFM studies, magnetic force microscopy, and you know that studies we could see magnetism at all the tips of these nanowalls. So why are the tips only ferromagnetic? Of course, you know that MFM was contested. Many people said that this is more of topography. Very difficult to separate the magnetism and the topography, the MFM measurement. So you have to do it at different heights and show that it still continues. And so it's not a topographic effect, because topographic effect dies 1 upon r square, but the magnetic remains linear. So we showed that, and then to prove that there's actually true magnetism. But still I did another experiment in Northwestern University, where they had a facility where they could change external magnetic field outside MFM. And when I did that, I could see that the tips of the walls of my nanowalls were purely magnetic with a very good high resolution magnetic force microscope. And when I changed the external field, the direction of the field, then I saw that this, yeah, okay, right, okay, I'll finish in a couple of minutes. Yeah, sure, sir, thank you. Okay, the field of direction. So you can create a magnetic field. So now I have electrons, I can change the band gap, I can do so many things. Then we thought it'd be a wonderful material for water splitting. So can we do water splitting with that? With the efficiency, we know this whole picture of how you can break hydrogen and oxygen in a water. So we set up the electrolysis system. Then, of course, I'll jump this very interesting result. But let me tell you, eventually, let me close here by making some very interesting. We have grown indium nitride also with very high mobility. Electron mobility is equal to that of theoretical, because this is important to make indium nitride for terahertz applications. Okay, so that kind of a material also was able to make. So in some sense, let me conclude here by telling, see, what is the beauty of the future of research which is going on to happen, which I think all young students, research students and young faculty should take up, is combining the standard properties of materials with the nanostructures. And as I can show here in our experiment, it can do amazing miracles, right? As I said, one material is behaving all the three as an insulator, metal, and the semiconductor, and the mobilities are increasing. While I get metal-like properties, I can also see semiconductor-like behavior. Amazing. So these can lead to tailor-making materials of whatever we want to do. So this convergence of bandgap engineering semiconductors and the size-dependent properties of nanomaterials in this particular experiment. But similarly, many other materials can also be done, which can lead to novel properties, novel phenomena, and applications. I'm sure such properties will be discussed in the rest of the day, and also probably in the future in all the research places. So now I thank a lot of people here. Of course, one Professor Rao, and then my collaborators there, Wagmare, Chandrabas, Dravid, and Mehta, and of course also my students who are the actual people who have done this work. I've shown only the list of my students who are involved in the particular work which I've shown here, and a lot of technical assistance, because we use a lot of sophisticated instrument. I want to thank all Jay, Srinath, Mahesh, Prajwal, Sachin, Jagdish, Osmani, Pattar, everybody for helping us in our technical experiments, because they play a very important role in doing reliable experiments. So I thank you all very much for tolerating me and my work for some time. And I apologize to the organizers that I took a little bit longer time than I was expected to. I'm sorry. Okay. Right. Okay. Anything? Okay. Right.
Thank you so much, sir. I think you actually throw a lot of light on a lot of concepts here, sir. And thank you so much for introducing so many new things, and also giving so much of good suggestions for the young teachers like us. And we definitely will take it forward, and we will try to implement most of them, sir. Thank you so much.
Thank you. Yeah.
Thank you very much, sir.
Thank you. My whole idea is hopefully to tell students, young people, there are a lot of exciting things which are going to happen in material science by combining material properties and nano properties in the coming future. So this is an exciting period to be in research for, and we are getting old, but I want the younger generation to come up and take this up very seriously. Thank you.
Congratulations, Professor Shiv Prasad. A wonderful presentation. I think we are quite excited to take up new research areas based on your very inspirational presentation. It's really nice to hear from you. Thank you so much.
Thank you, sir. Thank you. Always a pleasure to talk to you. Thank you very much. Yeah.
Thank you. Okay. So taking it forward now, it is very important to have the person who has presided today's program. I now request Professor N.K. Loknath, Director, PME Board, University of Mysuru, to present his presidential remarks. Sir, please, over to you, sir.
Yeah, good afternoon to everyone. So there is some
Good afternoon, sir.
network issues. Can you hear me? There is some network
Yes,
issue.
sir.
Yes,
Yes.
this is a picture. Anyway, I will talk. So it's good morning to everyone. Good afternoon to everyone, because already it is 12 o'clock now. And
Sir, sorry, sir, we are not able to see you. Sorry, sir. Mr.
some
Loknath, we
network
are not able to see you. We would like to see you. Say to hello. We would like to say hello to you, sir.
some network issues that I cannot able to see my camera.
That's all right, sir. That's all right.
Okay.
That's all right.
And Dr. Shiv Prasad, Dr. Yelamagar, Dr. Midhu, and Dr. H.S. Nagendra Kumar, the principal of the college, Dr. Sridevi, convener, Dr. Kanganaswamy, coordinator, IQAC, faculties of the college, students. So today, it is very interesting to speak about the material science. So Professor Shivaprasad has given us a wonderful talk covering a lot of things on material science. So he covered most of the topics which can be covered under the material science subject. So material science is a multidisciplinary field that involves the study of materials, structures, properties, and performance. This field has been significant advances over the years and has played a crucial role in shaping the modern world as we know it. The understanding of the properties of the materials has allowed us to improvise, incorporate, and explore novel applications that are immensely contributed towards the advancement of the humankind. In the last decades, we have witnessed that material science has shown some remarkable developments and had profound impact on a wide range of industries. So one more significant advance has been the area of nanotechnology. The development of nanomaterials, which has opened up new avenues for innovation and has the potential to revolutionize the way we think about materials. As there are students out there, I would like to make them to happy that why these nanomaterials are showing a lot of applications. So those materials are really unique properties and behavior due to their small size, and they have found applications in wide range of areas, including energy storage, electronics, and biomedical applications, which I have seen from the Professor Shivaprasad talk. So material science has also been in the development of smart materials. You are using smartphones, so you should have to have an idea of what is smart materials that are able to change their properties in response to changing their environment. With the world's growing demand for energy, the need for more efficient and sustainable energy sources has become need of the hour. In this regard, materials such as silicon, germanium, etc., have been used to develop new and more efficient solar cells. Additionally, recent researchers have also developed new battery materials with improved energy density and stability, which are essential for the development of electric vehicles and other energy storage systems. And also, we should know about when you are talking about nanometers, so nanocomposites, these are the class of materials that are made up of at least two distinct components. The unique combination of properties that arise from the combination of these components results in materials with properties that are superior to those of the individual components. So one of the most important benefits of nanocomposite is their improved mechanical and physical properties such as strength, stiffness, and thermal stability. For an example, the addition of nanoscale reinforcements such as carbon nanotubes or carbene or graphene to polymers can result in material that are significantly stronger and stiffer than the polymer alone. Nowadays, the wastewater treatment is a critical issue that affects both the environment and human health. And the development of more efficient and effective water treatment technologies, which is essential for ensuring a sustainable future. Nanocomposites also have potential applications in the field of energy. The incorporation of nanoscale materials such as metal oxides into polymer matrices can result in materials with improved energy storage capabilities. These nanocomposites can be used as supercapacitors, hydrogen production, ammonia production, carbon dioxide reduction, and lithium ion batteries, which are very essential for the development of clean energy technologies. The development of polymeric nanocomposites are now extensively used for drug delivery systems. So many experts in the field of material science, such as my friend Professor Shivaprasad and Dr. Nanjangud and Dr. Midun, will be sharing their knowledge, and I am sure that discussions will inculcate the intuition and give you new innovative ideas which will be very useful for your research or project work. In conclusion, material science has come a long way since its inception and has made a significant impact on our lives. From nanotechnology to smart materials, and from energy to biomedical engineering, The advancement in this field have opened up new opportunities for innovation and will continue to shape the future. It is a field that holds immense potential for further development, and I am confident that we will continue to see exciting advances in the years to come. I appreciate the efforts put up by the JSS College of Arts, Commerce and Science in organizing the one-day national webinar on the advances in material science, which will benefit a lot of young researchers, teachers, and students. I wish them best of luck. Thank you all.
Thank you so much, sir. Now, I request Dr. B.K. Kendaganaswamy, IQAC Coordinator, JSS College Nanjangud, to present the vote of thanks. And post the vote of thanks, we will have the technical sessions. So kindly hold on. Sir, over to you.
Thank you, Ullas. At the outset, I offer my humble pranams to the Guru Parampara of Suturmat, my sincere pranams to the divine soul of His Holiness Jagat Guru, Shri Shivaratri Rajendra Mahaswamiji, the founder president of JSS Mahavidyapita. My humble pranams to the lotus feet of His Holiness Jagat Guru, Shivaratri Deshikendra Mahaswamiji, the present president of JSS Mahavidyapita. Now I am glad to propose vote of thanks for all making the webinar meaningful and convenient. I thank Professor S.M. Shivprasad sir for his words of enlightenment as a keynote speaker. Thank you very much, sir. I would like to thank Professor Nikhiloknath, Director, PME Board, University of Mysuru, for his precious remarks. Thank you very much, sir. I also thank the speakers of technical session, Professor C.V. Elamagat sir. Thank you very much, sir. And Professor Mithun Dominic sir. Thank you very much, sir. I thank all officials of College Education Division of JSS Mahavidyapita for their constant support and encouragement. I thank our beloved principal, Professor H.S. Nagendra Kumar sir, for his support. Thank you very much, sir. I also thank the convener of the program, Professor Sridevi Devangaundar, and the organizing committee members. Thank you very much. I also thank all the faculty members and non-teaching staff of our college for their valuable support. My heartfelt thanks to Sri Ullas of Diksoochi team for his logistic support. Thank you very much, Ullas. My personal thanks to all the participants of the webinar who have registered in large number. Thank you very much for your support. Thank you one and all. Thank you very much. Over to Ullas.
Thank you, sir.
Thank you, Anna.
On behalf of the college, I personally thank you one and all in the inaugural session of the webinar.
Thank you very much.
Now I request Srimati Deepali MS, Head of Computer Science Department, JSS College Nanjangud, to give the introduction of our resource person, Professor C.V. Elamagat.
Oh, hold on. Good morning, everybody. I think you have to give a good afternoon, rather. You have to give a small break to the audience. I think it is too long. Give a small break. Maybe 10-15 minutes break should be there. Otherwise, very difficult to concentrate. Okay. Having heard such a wonderful lecture by Professor Shivaprasad, very difficult to digest the kind of matter he has presented over. So give a 10 minutes break. Let them refresh and come back. Okay.
Thank you so much, sir.
I'm ready. By the way, I'm ready. But I thought that break.
Thank you so much, sir. Your support is very important, sir. Thank you so much for your
and I'll be online all the time. I'm here. You just
thank you so much,
call
sir.
me. I'll be okay. I think exactly 10 minutes we can resume. Okay.
Definitely, sir. We'll do
it. Is my humble request that we should give a break.
Yes, sir. Yes, sir.
Okay.
It's a valuable suggestion. Thank you so much, sir.
Thank you, sir. Thank
So,
you.
participants, we have our technical presenters and speakers ready with us. So as you have seen and you have been hearing for a very long time, let's take a small break. We definitely have the support of Elamagat sir here. So we'll take 10 minutes of break and we'll come back.
Exactly 10 minutes. Ask them to come back exactly 10 minutes. Okay.
Yeah, exactly.
Otherwise, I'll be presenting the work that we have carried
definitely,
out
sir.
in recent times.
So as you all know, if you are missing out even a single minute also, it would be very difficult to come back and connect ourselves with respect to the flow of knowledge that will be going through this seminar. So kindly come back exactly in 10 minutes. We'll resume the session at 12:24 p.m. Thank you so much.
Hello. Am I audible?
Yes, sir, you're audible, sir.
Yeah. Can you see my presentation?
Yes, sir, I can see your presentation.
I'll put. Yeah. Can you see my presentation?
Yes, sir.
Okay. Great. So I'm audible and my presentation is very clear.
Perfectly
Right.
right, sir.
Then can we move on if the time is? We are done with the time.
No, sir,
Can we
another
move on?
3 minutes is there, sir. We'll give
All
another
right.
3 minutes.
All right.
Okay.
Thank you.
Thank you, sir.
Welcome back, everyone.
A very good afternoon to one and all. My humble pranams to Sutturu Guru Parapare. It gives me an immense pleasure to introduce Dr. C.V. Yellamagar. Dr. C.V. Yellamagar is serving as a scientist in the Center of Nano and Soft Matter Sciences, Bangalore. He has obtained his master's degree in chemistry and PhD in organic chemistry, both from Karnataka University. Invited scientist, he has been invited to USA, Canada, UK, Germany, Japan, Taiwan, Korea, and many other countries for presentations and collaborative research work. He has published over 225 research articles, both in national and international journals. He has authored a chapter in a book. He is a recipient of 11 national and international patents. He has supervised 13 PhD students and 7 postdoc students. He has been enlisted in the Stanford list of top 2% scientists in the world. His research experience encompasses the synthesis of natural products, heterocycles, and a wide variety of self-assembling molecules, especially liquid crystals. He is a recipient of many awards to his credit, namely CRSI Bronze Medal, Chemical Research Society of India, IISc Bangalore 2021, CRS Silver Medal, Krishnan Rasayan Sanstha, Vidyasagar University, West Bengal 2020, FRSC Fellow of Royal Society of Chemistry, UK 2019, MRSI Medal, Material Society of India, IISc Bangalore 2019, LSE Gold Medal, Indian Liquid Crystal Society 2017, Sri C.V. Raman Young Scientist Award from Government of Karnataka 2005. As a principal and co-principal investigator, he has undertaken around 9 CSR, UGC, SERB, and Tata Steel sponsored projects. We are elated to have you, sir, with you. I once again welcome you, sir. Thank you. Over to you, sir.
You're able to see the presentation?
Yes, sir.
Yeah. Madam, your name, please. The one who introduced me.
So myself,
Your name, please. Your good name,
Deepali,
please.
sir.
Come again, please.
Deepali, sir.
Yeah.
Deepali.
Madam Deepali, thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. At the outset, I think it's my pleasant duty, and it's rather my religious duty, to submit myself and my pranamas to Sri Sutturmatta Swamijis in particular. I would like to put my Srisastanga Namaskara to Jagadguru Sri Shivatirtha Shivayogi Mahaswamiji and Jagadguru Sri Shivaratri Deshikendra Mahaswamiji. With this, let me proceed with my presentation. At the outset, I would like to once again express my deep sense of gratitude for giving me this wonderful opportunity to participate in this one-day national webinar on the topic entitled Advances in Material Sciences, organized by JSS College. I'm particularly indebted to Professor Nagendra Kumar, who is the principal of this college, and Professor Kendaganna Swami and Sridevi Girigowda and other organizers of this particular event. And we have heard a wonderful lecture from Professor Shiva Prasad, and I think he has covered most of the aspect of the material science world. I don't see he has left anything, but today I'm going to talk to you about one of the fascinating aspects of science. This fascinating aspect of science, it is there right from the beginning, right from the evolution of this world, and it has been intensively seen. This particular science is being seen or followed, or it is being realized in India. We call something word invisibility, although physically somebody is present, but they are not. We are not able to see them. For example, God or goddess, we feel that they are there around us. I'm a spiritual man, so therefore I feel that God and goddess are our Guru we say. All of us are there around us, but we'll not be able to see them. That's what we call invisibility. But let me put it in a technical manner in these presentations and let you know what is it all about. Today, as I already declared, today I'm going to talk to you on one of the ongoing research projects in our laboratory. Since about a decade ago, we started this particular project, and recently we have been made some good progress as far as this particular research field is concerned. Today, I'm going to talk to you about functional soft nanocomposites for science and technology of invisibility. Professor Shiva Prasad and others have already spoken about composites, different types of composites. Well, as all of you know, if you consider a material, which is composed of chemical constituents, chemical substances, you cannot have the number of property one would be expecting for different applications. That is very well known. You take a material that has the ability to exhibit a particular property, that particular for particular applications. Suppose if you want to come up with the new materials and you are expecting them to show a number of properties for different types of applications, right from, say, for example, a material you have that should exhibit double refraction or thermochromism, photochromism, and other properties like semiconducting behavior whatsoever, all Professor Yoprasa already mentioned. So nowadays, what is happening is we have realized that properties, the number of properties, they cannot be expected from a single component system. Therefore, what has come up in the recent day, the very nice way of doing is developing composites. What does it mean? You take different types of material, develop a composite, so it becomes a one material and it exhibits a number of properties. I shall repeat as far as the students are concerned. Well, you have a material that cannot give you all the properties, but if you try to take different materials, okay, and try to combine them so as to realize what are known as functional composites. Today, I'm going to talk to you about such a composite, or we have developed different types of composites, wherein generally what you see is people try to make composites using hard materials. Generally, most of the materials we use in composites are hard. Today, I'm going to talk to you about an entirely new concept that you take soft materials and nanomaterials, combine so as to realize what are known as soft nanocomposites. It has come up in the last 4 or 5 years or so. So this we have religiously following this kind of research work in our research laboratories, and we have been able to get some very interesting results as far as this soft nanocomposites are concerned. As I mentioned, today I'm going to talk to you about functional soft nanocomposites for science and technology of invisibility. What is invisibility? I shall come back to that point a little later. This work has been carried out by one of my very promising and very hardworking student, who is in the forensic department in the state, Karnataka state, namely Dr. Sachin A. Bhatt. He has recently left the lab and he has joined there. This work could not have seen this height without the help of or the fruitful collaboration of our colleagues, Dr. Shankar Rao, Dr. Geetaji Nayyar, and Dr. Krishna Prasad. Well, in essence, today I'm going to talk to you about the molecular design, synthesis, and characterization of a 3 series of soft nanocomposites, the general structures of which are shown here. As you can see, what exactly we have done is we have taken gold nanoparticles and we have stabilized them with organic ligands. By no means these organic ligands are ordinary, that they are not simple organic ligands. I think all of you know, all the researchers, all the research students or researchers or MSc students, you know that generally the gold nanoparticle or any metallic nanoparticle can be stabilized by coating them with the organic ligands. You take, for example, amines, you can take amines, thiols, and carboxylic acids to stabilize the gold nanoparticles. That's exactly what we have done, but with some systematic selection of organic ligands which stabilize nanoparticles. As you can see here, in the first structure, this is the structure. So in the first structure, what we have done is we have taken a gold nanoparticle around which we have attached ligands. These ligands are nothing but liquid crystals, means they exhibit liquid crystallinity. So here the central gold scaffold is there, and then to this we have attached organic ligand, and in this ligand we have only one phenyl ring, and at the end we have cholesterol as shown here. Wait, you are able to see my marker?
Yes, sir.
Hello? You are able to see the marker?
Yes, sir.
Yes, sir.
Yeah. There is no problem whatsoever. The presentation, you are able to see, all of you are able to see?
Yes,
Yes,
sir.
sir.
Okay, fine. Fantastic. Okay, let's proceed. Okay, so now, in the second thing, what we have done is we have taken a ligand that has a biphenyl ring, and in third, we have taken a ligand that has azo. Mean systematically, we have varied the structure of ligands that those are liquid crystalline and stabilized gold nanoparticles, and try to study the structure property correlation, and we try to explore the possibility of obtaining the properties that are associated with invisibility. Well, this work was inspired by one of Nature Material paper. They developed soft metamaterials. Okay, so based on this, we began this work somewhere in about 2016. Well, there are before proceeding to my actual presentation, I would like to draw your attention on the fact that there are global concerns. We have n number of challenges as far as the science or technologies are concerned. To begin with, we have a series of problems as far as the potable water is concerned. In the days to come, I think all of you are aware of the fact that we run out of drinking water. So we need to do something about it. Well, this is the point to say that we have a number of research centers all over the world, including in Karnataka, like IAC, GNCER, and like RRI. You have so many research centers. Well, the first question is, what do they do? This is very important as far as the students are concerned. You need to understand that there are global concerns. Therefore, all these research organizations put in effort to face these challenges in science and technology. For example, potable water, be it with food and agriculture, we have food crisis, shelter, health, safety, energy, pollution, climate change, and global warming, nature and animal conservation. No, most of the time, or most of the research organizations, they try to focus their attention on the hot topics like health, safety, energy, and pollution. Okay, so scientists, as I mentioned to you, scientists across the globe are engaged in the design and preparation of functional materials to address the problems that are associated with water, potability, purification, controlling the hardness, removal of toxic metal ions, be it on the surface level or in the ground state, ground level. So we try to remove the toxic metal ions like arsenic and mercury. That's one of the challenges we are facing in India. And health, especially in these days, you know about COVID-19 situation. Well, if we were to prepare, develop good medicines for this kind of a virus, which is very adamant, we could have been saved 2 years. We have lost 2 years. I mean, we're sitting at home doing nothing. We lost 2 years. So we could have been, if one were to develop proper medicine, antimicrobial medicine, then we would have been, we could not have faced this problem. So when it comes to energy, we have problems like storage, generation, conversion, transport, and conservations. So we are trying to put in efforts, as Professor Shiva Prasad mentioned, we're trying to put in efforts to address all these concerns, be it with the storage, generation, conversion, transport, and conservations whatsoever. When it comes to food and agro industry, so I think compared to my parents, I'm a bit weak. Compared to me, the recent students are a bit weak because we are not getting food that has the nutrients. So we're running out of nutrients. So that's one of the another major challenge. Well, if you are strong, if you are healthy, then only you can do something. So therefore, now a lot of focus is, a lot of attention is being paid to come up with the crops that have lots of nutrients. And there should not be any toxic. We spray these medicines like, in the fields, we spray, but they are highly toxic and free from chemicals, and these chemicals generate radicals. So therefore, there are challenges as far as we scientists are concerned. We need to do many, many things. To the best of my knowledge, I've been in the field about 40 years or so. To the best of my knowledge, it is we can address all these issues, all these concerns, global concerns, with the help of materials what are known as functional materials. So functional materials, as Professor Prasad has already mentioned, that functional materials are very, very important as far as the present scenario is concerned, be it with water, health, energy, food and agro industry, or environment. So now I'm taking you to the altogether different world. Now, presently, there are so many concerns are there. So scientists are working on different fields, but I would like to talk to you about one of the fascinating aspects of science that has recently come up. So scientists are focusing on highly functionalized artificial materials. They're called metamaterials. The highly functional artificial materials are called metamaterials. So they have a number of applications. But I'm going to talk to you about the usage of metamaterials in one aspect, that is invisibility, or clocking objects or making them appear invisible. What do you mean by invisibility? It is nothing but clocking objects, making them appear invisible. I shall come back to that point a little later. The object or subject doesn't really disappear. It is present but cannot be seen. This cannot be seen by your eyes. So let me tell you what are metamaterials. Metamaterials are artificial materials that possess novel functionalities with exotic properties. I shall repeat, metamaterials are man-made materials. They are not natural materials. They are man-made materials. They are artificial. Therefore, we call them artificial materials that possess novel functionalities with exotic properties. For example, they have incredible ability to manipulate light. They interact with the light in an altogether different manner. We know about light and interaction, the interaction of light with different objects. We all have learned about it. But as far as the metamaterials are concerned, they have altogether different way of interacting with the natural light. It could be any kind of laser light, or it could be natural light, whatever it is. I shall come back to that point a little later. Metamaterials, in particular, metamaterials. I think this word, I think you should catch up. I think you must note down metamaterials. Metamaterials are highly functionalized artificial materials. They have a number of properties. For example, in the universe, you have different materials, especially I'm talking about transparent materials. They have certain refractive index. For example, air has a certain refractive index, water has a certain refractive index, and you have a number of materials, they have their own refractive indices. Now, when you really talk about the refractive index, please note that all of them have positive refractive index. I shall repeat, they have a positive refractive index. Water has a positive refractive index, or oil has a positive refractive index, or water has a positive refractive index. Unlike that, metamaterials have a negative refractive index. It means that you can develop a material. We can develop a material, highly functional material, that's called a metamaterial, that has a negative refractive index, that is against the nature. Most of the material what you have, I mentioned, they have a positive refractive index. So therefore, such materials manipulate electromagnetic radiation, that is light. It's simply such materials bends light backwards. Okay, with this brief introduction, let me show you some. You are able to see the play here? You are able to see the play? Hello, somebody should respond. You are able to see the
Yes,
picture going on?
Yes, sir. We can see, sir.
Yeah. Okay. I think this is one of the very interesting, very exciting film, Harry Potter's. You can see the main character is moving in a library with a lamp. Lamp is seen, his hands is seen, but the body is not seen, although body is moving. So that is what is called invisibility. Look at it carefully. A body is moving, a main character is moving with a lamp. He is stepping forward. Body is moving, although body is there, but physically it is not seen. You are able to see, all of you are able to see?
Yes,
All
sir.
of you are able to see?
Yes, sir.
Yeah, you can see the lamp and hand, but not the body. Although physically body, it is there. So this is what we call invisibility. Okay, so some part of the body is hidden or it is not seen. Although physically it is there, the main character is there, but you're not able to see the main character or the body of the main character. Only the hands and lamp is seen. Although the light is falling on this body, but you're not able to see. Okay, my presentation is like this. In our day-to-day life, we come across so many things, or you'll be sitting, you will be watching, you are watching my presentation, you are hearing me, you are able to watch friends around you, you are able to watch, you are able to see the chair, table, the walls around you, computer, what you have. My the first question is, why are you able to see the things around you? My first question. The answer is very simple. You know, answer is extremely simple. The light electromagnetic radiation, which is falling on us or any object that is around you, the light which is falling on certain object or the things around you, what happens is that this light, beam of light, either gets scattered or reflected. So the reflected light comes to your eyes. Therefore, ladies and gentlemen, you are able to see the objects around you. Am I right? So you are able to see things around you because the things around you have they're interacting with light. So light is falling on them. Therefore, light gets scattered or reflected. So the reflected light comes to your eye. So therefore, you are able to see. Now let's say that although physically something is there, if by some means, by doing some scientific experiments or some technology, if the light which is falling on particular object, the objects around you, if it doesn't come to your eye, then you are there, then we will talk about invisibility. That's exactly what is happening in this movie. Let me show you another a picture. See here what exactly is happening. Well, the main character is moved in the library, that the main character is coming, Harry Potter is coming, and now see what exactly is happening. He is pulling out the sort of a gown or a cloth, and the moment he removes this the thick cloth, the body is seen. What does it mean? It means that as long as this cloth was on him, on the main character, you are not you are not able to see him. I shall repeat. As long as the gown was on the main character, you are not able to see him. Only the hand and lamp was seen. The moment the main character removes his gown or the thick cloth, you are not able to watch this, all of you?
Yes, sir.
Yeah, fine. The moment is, you are able to see the moments?
Yes, sir.
Yes, sir.
Okay, yeah. The moment you take off, the main character takes off the gown, you are able to see the main character, that's Harry Potter. What does it mean? So this cloth, what was he wearing on his body? It has something to do with the metamaterials. I shall repeat. This gown is made up of metamaterials. Means this gown has altogether different property than usual materials. This gown is made up of metamaterials. I don't know in that picture what was it. It's only the visual effect, but in the context of my presentation, I would put that particular cloth under the category of what are known as metamaterials, and that have a negative refractive index. Means the metamaterials, this gown is made up of metamaterials. For example, I'm assuming. So the way light interact with this particular gown is totally different from the other objects. Okay, what is it? What exactly happens? So let us move on to other scene wherein you can clearly see. In the world of Harry Potter, invisibility clocks are made from the hair of a magical creature called demigus. Presently, they are made by metamaterials. You can see the two friends in the picture of Harry Potter. They were wearing, what is called gown made up of metamaterials. I guess for my own comfort to make it convincing presentation. The moment they remove that gown, they are visible. Until and unless they are not visible, as long as the gown was on them, they become transparent. Okay, what does it mean? It means that when, as I mentioned to you, when light falls on any object, for example, on us, okay, so if you are sitting in front of me, you are able to see me, or I'm able to see you, because light which is falling on me either gets scattered or reflected. The light which is reflected from my body comes to your eyes. Therefore, ladies and gentlemen, you are able to see. I think I made it very clear. Once again, I tell you what exactly it is. You are able to see the things around you. It could be anything. You are able to see the things around you because simply light is falling on these objects. Light is getting scattered. Don't worry about scattering of light. The light which is falling on the things around you gets reflected. Therefore, you are able to see. Now, by some means, if you are stopping the light which is getting scattered or getting reflected by some means, then you are there. Then we can talk about invisibility. I shall repeat. The light which is falling on a particular object, by some means, if you can stop the reflection of light, instead of bending, instead of that, light should bend around an object. Suppose light all falls on me, okay? So my body is such that it reflects the light. But if my body is tuned in such a way that it doesn't reflect the light, instead it makes the light which falling on me to take a deviation, then I become invisible. I shall repeat. Suppose if you are standing in a hot sun, we are able to see you because light which is falling on you gets reflected. Therefore, I'm able to see you or your friends. I don't want to do that. I want you to be invisible. What is to be done? It's very simple. Very simple. The light which is falling on you should not be made to reflect. Instead, what you should do is you should develop a technology wherein light takes a deviation from the body. Then you become invisible. So this is what is all about the invisibility. I hope you understood. Once again, to catch your attention, let me talk to you about the design and synthesis of a new generation of materials. They're called metamaterials. They have n number of applications. Metamaterials, please note, ladies and gentlemen, metamaterials are artificial materials. They are made up of metals and plastics. They are man-made substances, okay? These man-made substances have the properties that are not found in nature. I have been repeatedly focusing on this point. Natural materials, the way light interacts with natural materials is entirely different from the way light interacts with the metamaterials. For example, they manipulate light waves by blocking. Please note the point. They manipulate light waves by blocking, absorbing, enhancing, and bending. In particular, to be very technically correct, they exhibit what is known as negative refraction. I think all of you are aware of what is refraction of light. Negative refraction, epsilon near zero, ENZ property, perfect lensing, and hyperbolicity. Given the very fact that my particular presentation or my research work is something to do with epsilon near zero, let us see what is this ENZ. It is not difficult to understand. Let us try to understand what is epsilon near zero, okay? Epsilon near zero materials exhibit, please note, this is very, very important point, okay? Epsilon near zero materials exhibit a transition in the real part of the dielectric permittivity from positive to negative value as a function of wavelength. I hope you got my point. I shall read again. Epsilon near zero materials exhibit a transition in the real part of the dielectric permittivity from the positive to negative value as a function of wavelength. So this is what is being accomplished as far as our materials are concerned. Although we have realized as many as 12 different soft nanocomposite, among them there are 4 materials they show epsilon near zero characteristics. Well, this is what exactly I said. When we see things we see things because they reflect light into our eyes. This is literally the only way we get to see the things around us. All objects we see either create light or reflect light. So what do you mean by this? By some means, if you can stop the light which is falling on you or any object for that matter, if you can stop the reflection of light, then that becomes invisible. That's what I intended to say. Okay, let me have a few words about the kind of research activities that are taking place at the Center for Nano and Soft Materials Sciences. This comes under the administrative control of Department of Science and Technology, Government of India, and indeed JNCR, RRI, and we are all sister concerned. We all come under the JNCSR. We and RRI comes under the administrative control of Department of Science and Technology, Government of India. Right from the inception of the center, we have been focusing on the molecular design, synthesis, and characterization of soft materials, in particular liquid crystals. Those can be used for display technology. Ladies and gentlemen, all of you are aware of the a small panel that is present on your wristwatches, your calculators, your mobile phone is very, very important. Your mobile phone are composed of a small, bright display that's called liquid crystal display. So we have been trying to, what is liquid crystal display? The liquid crystal display is nothing but that you use in your laptop computer. It is there. These are the small devices which is there on your mobile phone or what, a calculator or your wristwatches. So you have a small panel that's called liquid crystal display, that's popularly known as LCDs. So in these LCDs, we use organic molecules. So we design, so most of your, the cost of, that you can have a mobile phone ranging from say 500 rupees to lakhs of 10 lakh, 20 lakh, something like that. So the cost of your mobile phone or wristwatch or your laptop depends on the kind of organic molecules you use, which act as optical shutter. Means we design organic molecules such that they exhibit all sorts of properties required for the development of a liquid crystal technology, and we see that the cost is reduced. So that is our business here. What we do here, we design new molecules that are cost effective, but at the same time show all the properties required for the development of a display called liquid crystal display. We also design and synthesize liquid crystals. Those can be not only used for display technology, but also solar cells. So here I must mention that Professor Sivarama Krishna Chandrasekhar, who is a very popular physicist, who is no more, unfortunately, who is a nephew of Sir C.V. Raman, worked on discotic liquid crystals. So these discotic liquid crystals can be used for the fabrication of solar cells. Well, in the recent time, in the last 2 decades or so, we have been working on gels in association with our colleague, Dr. Geeta Nair. We have been able to develop some gels. What I said is, in your LCDs, liquid crystal display, you use organic molecules. Okay, there are some issues, still there are some issues with such displays. What we try to do is we make gels and try to use them as far as the LCD technology is concerned. So to some extent, we have been successful and we have patented this work. Ladies and gentlemen, in the recent times, we have been trying to carry out a perfect marriage between nanomaterials and liquid crystals so as to realize what are known as soft nanocomposites. Well, let me put it in this way. Nanomaterials, as Professor Shiv Prasad already mentioned, nanomaterials are very hard materials and they have a number of properties. On the other hand, liquid crystals, by name itself, says that they are soft materials. What we are trying to do is we are trying to carry out a perfect marriage between these two. What does it mean? Let me put it this way. I take a butter, which is soft. I take the stone powder or sand. I try to mix them. What happens? There is a phase separation. As butter cannot go with the sand, right? Or fine stone powder, which are of the nano size, cannot go with the butter, although butter is soft. There's a physical, when you melt, there's a physical separation. Here, what we are trying to do is, we are trying to make a perfect blend. Means there should not be any phase separation. When I take nanomaterials, stabilize them with organic molecules that show exhibit liquid crystal property, you get a material where the phase separation is not seen. That's what we call the perfect designing, or perfect using our knowledge of organic chemistry and nano systems. We can realize new materials. They are called soft nanocomposites, wherein there is no question of phase separation. So this is the, you use your chemistry knowledge and try to do this. What does it mean? It means that we develop. You are able to hear me? Somebody should respond.
Yes, sir. We are hearing you.
Clearly?
Yes, sir.
Okay, fine. Am I audible clearly?
Yes, sir.
Yes, sir. You are all completely
Fantastic.
audible.
Yes, sir.
Fine, sir. Fantastic. You are able to see my screen?
Yes, sir.
Okay, fine. Fantastic. Let's proceed. And what exactly we are trying to do is, we are trying to overcome the problem of the phase separation. We are taking ultra fine hard materials, trying to associate them with soft materials, which are basically organic molecules. Okay. Then the question would arise, obviously, in young minds, question would arise, sir, why do you do this? You are taking the ultra fine hard materials, and you are taking soft materials, you are trying to combine them. Well, as name itself suggested, we are trying to design and develop soft nanocomposites. Why am I doing this? What is the purpose? Okay, composites, all right. To this particular event is a apt presentation, I think. I'm developing soft nanocomposite. For what? Well, you are developing for what? There should be some reason. There should be some motivation to develop such materials. What is the motivation? Motivation is very simple. As I mentioned to you, or I'm mentioning it to you now, liquid crystal form the basis of life. The liquid crystals which form the basis of our life have n number of properties, n number of different exotic properties on one hand. On the other hand, we have nanomaterials. You have different types of different types of nanomaterials, right? Ranging from metal oxides to metal nanoparticles. You have a range of nanomaterials. They have, as Professor Shiv Prasad already mentioned, he took the example of gold, starting from a tiny gold to the silver film, the metallic gold film. You can see, depending upon the size, their property vary. So what we're trying to do is, the nanomaterial, we have understood that nanomaterials have a number of properties and liquid crystals have a number of properties. Therefore, if you combine the properties of both soft, you combine liquid crystals with nanoparticles, associate them, make them to associate with each other, so as to realize what are soft nanocomposites. The end result, the material which comes out as a soft nanocomposite, should exhibit the properties of both liquid crystals as well as nanoparticles. I shall repeat, these soft nanocomposites, which are new in the world now, they exhibit the properties of both liquid crystals as well as nanoparticles. So that is what is it. So this combination has given us some interesting result. Especially this has given us a result where it falls in the category of what is known as the science topic invisibility. So as far as I'm concerned, we have been working on presently soft nanocomposites. As I said, basically what we are doing is we have taken gold nanoparticles. Now we are also working on bimetallic systems and silver nanoparticles. What exactly we have done is we have taken gold nanoparticles, to which we are trying to attach organic molecules. They exhibit liquid crystalline property. So this is the area I'm going to talk to you today. Okay, and we have been also trying to develop composites for electrocatalysis. Especially, we are interested to develop catalysts that help in water splitting. You know that water is formed by the combination of H2O and oxygen. And this forward reaction is very easy, but backward reaction is very tough. Once water molecule is formed, nature makes the water molecules in a beautiful manner, but it's extremely difficult to come back. Okay, have the reverse reaction. Well, water is formed, H2O, but you cannot break the water bond that easily. H2O, okay, is a V-shaped molecule, is extremely difficult to break this molecule. That's what Professor Shiv Prasad was mentioning, including Professor, Professor C.N.R. Rao. He is very much interested in this water splitting, developing catalysis that can split water into hydrogen and oxygen. So I think most of the scientists are focusing, especially I think Professor C.N.R. Rao, I think Shiv Prasad agrees with me that Professor C.N.R. Rao has come up with a beautiful catalyst that split water into their nascent molecules like hydrogen and oxygen. Hydrogen acts as a source of energy. So now you must have heard about the vehicles which are run on hydrogen, and of course you have to put water. Water splitting will be there in that engine. So water split, hydrogen. There's evolution of hydrogen and oxygen. Hydrogen is let out. It's a nature benignant. Whereas hydrogen can be used as a source of energy in an engine. So that's what exactly we have been trying to do. And also we have been trying to develop, say, polymers, coordination polymers and metal organic framers so as to use them for the detection of toxic metal ions, toxic gases and explosive sensors and so on. As far as the new areas is concerned, during the past decade or so, we have been trying to develop reagents. Here I would like to talk about an incident that you must have heard about the explosion of ammonium nitrate in one of the, I will not take the name of the nation. Okay, so there's a huge explosion in some yard in one of the countries. The explosion was such that ammonium nitrate was piled up in tons. It was stocked in tons. But by some means, they were not able to recognize that it is potentially danger, that you cannot store any explosive materials. Okay. Now, the point is to say that if you take a salt, sugar, and ammonium nitrate, they look alike. I shall repeat. If you take in a test tube a sugar, a bit of a sugar, a bit of a salt, and a bit of ammonium nitrate, please note, students, especially, you cannot distinguish. Their nature is same. Okay. But how to distinguish whether the given material is ammonium nitrate or explosive, or it is a salt or sugar? It has happened recently in one of the airports, and I shall again, in the interest of security reason, I shall not reveal where it happened. A person was carrying white powder. He said that it is a sugar, prasadam. He got prasadam from some temple and he's carrying. But nobody noticed it. But that same person went to Aviation Ministry and said that I was able to take 1 kg of ammonium nitrate from this airport to that airport without any, security. Without any hassle, without any problem. It means that we don't have mechanisms in the airport or in sensitive places or places where a large number of people gather. There we don't have a mechanism to distinguish whether the given substance is the substance put in the bag or in some box is ammonium nitrate or sugar or salt. Therefore, what we have done is we have tried to develop a very small, very inexpensive material that's called coordination polymer. What I do is I take this coordination polymer in a solution in a mixture of a DMF and water, and take sugar, salt, or ammonium nitrate in 3 test tubes. When I add my reagent, that coordination polymer, which we can produce in tons, if I add a drop of this coordination polymer to the solution of a sugar, salt, and ammonium nitrate, there will be change in the color with regard to, there will be change in the test tube where ammonium nitrate is present. Just for the sake, and this has become very popular. We have been able to patent this work, and without any much of a botheration, we have been able to distinguish between salt, solution of salt, say sugar, and ammonium nitrate. Ammonium nitrate being a electron deficient system, it interacts with the coordination polymer. There's a formation of complex, therefore there is a change in color. So that's a simple approach we have made with regard to the detection of explosives are concerned. Using this technology, we have been able to develop reagent that can detect at least 6 to 7 explosives which are potent, which are used by people. I don't know, take their name, for illegal activities. Well, coming back to my presentation, this is how I intended to speak to you today. I shall rather touch upon important point rather than the technical details, because for students and for especially for MSc and research students may be boring. So in that context, I think our all teachers, professors who are sitting there may have to excuse, because I'll be touching upon very fundamental aspects. This is I'm trying to convince students what it is, what we have done. So you may have to forgive me. With that note, let me proceed. So this is how I intended to speak to you today. First, please, somebody has to alert me with regard to the time, because I have the habit of talking for a long time. Please, somebody has to remind me that I should stop talking. Okay, fine. Somebody should respond. Hello.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Please alert me when my time is up. Okay, please alert me. Okay.
Sure, sir.
Thank you. Thank you. Please be sharp. Okay. Okay. First, how much time I have, by the way, organizers?
Sir, another 5 minutes should be fine, sir.
5 minutes. Okay, that's done. Done. Okay.
Thank you, sir.
So this is the general overview of the talk. First, I'll try to cover the aspects of liquid crystals and see what is being reported, and then what are the results that are accomplished when you talk about the combination of liquid crystals and nanoparticle. Is my time is being cut, or what was the time given to me? I'm really surprised. Hello. Hi.
Hello. Can you hear me, sir?
Yeah. Please tell me how much time was assigned to me.
Another 5 minutes, sir.
No. What was the original time assigned to me?
45 minutes.
No, I have taken 40 minutes already.
Yes, sir.
Sure?
Yeah, sir. Another 5 minutes, it will be almost 50 minutes, sir.
Okay, then great. Okay,
yeah.
Fine. So then we'll see what is being done. Okay. In the interest of time, so liquid crystals are the intermediate state between the solids and liquids. They exhibit the properties of both solids and liquids. They, for example, they have orientation order, position order in 1 2 dimension. They exhibit double refraction. They are fluid and viscous. So fluidity comes from the liquid like property, and they doubly refract. I mean, they have double refraction. Okay, because they show anisotropic behavior in their optical, mechanical, electrical, and magnetic and elastic properties, they have been used in display technology. On the other hand, metal nanoparticles are ultra-fine species. They possess properties, as all of you know. They have large area gram, a stepped surface at the atomic level, and so on. Sometimes I wonder, I being a scientist, I have my own way of thinking. Sometimes I feel that nanoparticle represent yet another state of matter, or what. As I said, liquid crystal represents another state of matter. Likewise, I'm just thinking is of my maybe very weird way of thinking, but nanoparticle, I feel that they represent another state of matter. But one of the outstanding characteristics, okay, let me put it this way, liquid crystals have some outstanding properties. Liquid crystals flow like liquids. At the same time, they show what is known as double refraction. I shall repeat, liquid crystals show fluidity. They flow like liquids. At the same time, they show double refraction. Okay. Now, when you talk about nanoparticles, they show a very outstanding property that's called surface plasma resonance. Okay. This surface plasma resonance is very, very important. I'm sorry. So what does it mean? Here, if I combine liquid, I'm sorry. If I combine liquid crystals with nanoparticle, if I make liquid crystal ligand to associated central gold scaffold, then one should be able to realize what are soft nanocomposites. They exhibit the properties of both, like liquid crystals. They, at some point in time, they behave like a liquid crystal. At some point in time, they show the properties of properties of nanoparticle, in particular surface plasma resonance. In a sense, we have made materials soft nanocomposite. They are fluid. They flow like liquids. At the same time, they show double refraction, and also they exhibit surface plasma resonance. It's very important point to be noted is that any nanoparticle you take, they are stabilized by organic molecule. Well, they are stabilized by organic molecule. You cannot take these nanoparticles which are coated with simple organic molecules. You cannot put them into isotropic liquid state. the soft nanocomposites what we have made here in our laboratory, I can make them to exist in 3 different states, that those being liquid state, crystal state. If I heat them, they enter into liquid crystalline state. Then if you heat it, they go to isotopic state, means liquid state. So now I have soft nanocomposites. They are nothing but the nanoparticles coated with organic molecules. They exhibit liquid crystalline property. So these composites, they exist in 3 different states. And if you take them to the liquid state, is very, very important as far as the present technology is concerned. So the point was to see whether can we change the shift, or you know that in UV you can clearly see the SPR peak. Can we shift, say, from 500 nanometer to lambda max 500 nanometer, 600 or 700, something like that. So looking into that aspect, we try to coat them with liquid crystals to see whether we can drift it. So there are some ways. There are 2 approaches. One, you take nanoparticles and gold nanoparticles, mix them physically, but there is phase separation problem. So this is a method wherein synthesis of single component LC-NP hybrids, where functional LC molecules ligands are bound to central gold scaffold. This approach is highly promising. That's what exactly we have done. So let me skip all these things. Okay, let me go to what we have done exactly. See, this is what we have done. What we have taken is amines, and we have used auric chloride, AU3 ions. So here, amine not only liquid crystal ligand, which you see, it not only acts as a reducing agent, but also gets attached to the central gold scaffold. Here it's very clear that the ligands, liquid crystal ligands, which you use as amines, they not only reduce AU3 to AU0, but also they get attached to the central gold scaffold. So we have been able, this is a mechanism how the amine, primary amine, reduces AU3 to AU0. So these are the products. We have been able to make about 12 soft nanocomposites, and among them, the last one, this one, AZC3, AZC4, C5, and 7 showed the properties. So this is how we made. I take just a couple of 1 or 2 minutes. We take AU3, even that's what I am trying to say. The concepting idea is very important than what is when having the large number of equipments and all. I feel that even this kind of a chemistry can be done even at the university, just in the BSc laboratories or MSc laboratories. Look at it, what we have done. What we have done is we have taken dichloromethane, DCM, and aqueous solution, AU3 ions put in water. So you can see 2 layers here separated. Dichloromethane is here, and your water water containing AU3 ions is here. The moment you add phase transfer catalyst, the AU3 ions move to the organic layer, and now we take our organic molecule in DCM and add dropwise. You can see the clear, there is change. If you look at it carefully, you can see here, you can see the pink color formation. So that clearly indicates that the gold nanoparticle, the formation of gold nanoparticle, where amines reduce the AU3 to AU0, and these ligands get attached to the central gold scaffold. So once this is being done, leave it about for 5 minutes, just a 5-minute reaction. Take out the water layer and wash thoroughly this one with the dichloromethane, and evaporate the solvent. You will get what are known as soft nanocomposites. So we have characterized using different techniques. I shall not go into the details of this characterization. So, but this is very important that HRTM clearly established the fact that these compounds, established the fact that the average particle size is about 3.3 nanometer. Well, this is one of the very important slides as far as I'm concerned. You can see that once you burn the organic molecule, well, you have taken gold nanoparticle to which you have attached the organic ligands. And once you burn the organic ligand, see what is left. What is left is nanoparticles that they are helically organized. You can see this helical organization. It means that you can use liquid crystal phase as a templating agent to generate chiral nanoparticles, means the self-assembly of nanoparticle in a chiral way. You can see these nanoparticles are aligned. They are helically organized. So let me pass on this. Then important point to show is that, yes, this is the important slide, I think. Yeah. This is the one I was talking about, epsilon near 0. Sorry. Yeah. So this is the liquid crystal structure we have. This is the liquid crystal macroscopic structure. That means when you take your soft nanocomposite, which is solid at the room temperature, dark pinkish crystals. They are crystals when at room temperature. Rather they're amorphous. Some of them are crystalline. When you heat them, they melt into liquid crystal phase, and liquid crystal phase structure is like this. Means it is a helical structure. So this has shown ENZ property that was being established unequivocally by our colleagues, Dr. Geeta Ji Nair, in association with Amit Bharadwaj and Vimala Sri Durai. They established the property, that is epsilon near 0 behavior. These plots clearly demonstrate that these compounds show epsilon near 0. If Professor Shiv Prasad is around, when I presented this work somewhere in 2017, he was questioning, do you get the plots? Have the plots? That time we were not really aware of the different techniques that one can use to figure out the soft metabolic characteristics these compounds have. Now later on, with the help of Dr. Geeta Ji here, we have been able to establish the beautiful properties shown by these soft nanocomposites. Means these compounds can serve as metamaterials. That's all I wanted to say, ladies and gentlemen. What essentially we have done is we have taken gold nanoparticles and we have decorated them or stabilized them with liquid crystals which are functional. This combination has led to the products. They are called soft nanocomposites, and these soft nanocomposites are very, very interesting and promising, wherein we have been able to see the ENZ property. Thank you, one and all. Thank you for being with me. Thank you for listening to me. Thank you.
Thank you so much, sir. I think I have to add a few of the comments that we are getting in the YouTube channel as well. They have been very glad to listening to you, sir. So they have thanked you like anything. Many of them have put their feedbacks and they have thanked you for a wonderful session. And one of the participant has specifically mentioned about the photolysis of water in green plants is amazingly performed. So he has appreciated the work that your team has done. Thank you so much for all the knowledge that you have shared with us, sir. I believe.
Thank you very much. Thank you.
Yes, sir.
I hope people enjoyed, and
yeah,
I served the purpose. Thank you very much for giving me an opportunity. I think it's my pleasant duty to serve Suturmat. Anytime you call me, I'm ready to give my service, humble service. Thank you very much. Thank you.
Thank you so
much. Any questions? One or two questions are invited if anybody has.
Okay,
any questions, or you can post those questions to me. I'll be able to answer. It's my as I think all of you know that I'm very much interested to inspire students. I mean, at least I hope by this way one or two students get inspired to take up science as their main career. Thank you very much.
Yes, thank you so much, sir.
Can I take off? I mean, I have something.
Yes, sir. Yes. Thank you so much.
Thank
you so much, sir.
Thank you, one and all. Thank you
so much, sir.
Okay.
Yeah. Now I would like to request Sri Ravi Teja.
Yes, sir.
Yes. Assistant Professor of Physics, to now introduce our second resource person, Professor Mithun Dominic.
Good afternoon to everyone. Welcome to second technical session. It's my pleasure to introduce and welcome.
Sir, if you don't mind, Ravi Teja, excuse me. Yeah, there is an echo. I think they have multiple meetings should be turned off. Okay.
Wait a minute, sir.
Yeah, take your time. Take your time. Yeah.
Is it okay, sir?
Yeah, that's fine. Now you can start.
Okay. Welcome to second technical session. A very good afternoon to all. My humble pranams to the Suttur Guru Parampara. It's my pleasure to introduce and welcome Dr. Midun Dominic CD. Dr. Midun Dominic CD has been serving as Assistant Professor, Department of Chemistry in Sacred Heart College at Tevara in Kochi. He has completed his master degree in chemistry from United Christian College and has obtained PhD in chemistry from Cochin University of Science and Technology, Kerala, on the thesis titled Novel Nanocomposites applications and also and sustainable materials, green tires and rubber technology, polymer chemistry, biodegradable packaging films. He has involved in collaborative research work with scientists. He has published over 24 research papers in peer-reviewed journals. He has authored 7 chapters in a book. He has received many awards, namely CSIR, Flair Award, awarded by Higher Education Council, Government of Kerala, Dr. Dan Totakara Best Publisher Award, Dr. Sayarik Anthony Young Scientist Award, and Share Award awarded by Sacred Heart College, Tevara. He has been undertaken 2 projects as a principal and co-principal investigator funded by Government of Kerala. Welcome you, sir, behalf of our college. Now I request Dr. Midun Dominic.
Thank you.
Now I request Dr. Midun Dominic CD to deliver his speech. Thank you, sir.
Okay, thank you. Am I audible?
Yes, sir.
Yes, sir.
Okay. So first of all, warm good afternoon to all of you. It's my pleasure to deliver an invited lecture at JSS College. And at the outset, I would like to thank the coordinators and conveners of this webinar for giving me an opportunity to deliver the lecture. So am I share the slide?
Yes, sir, you can share.
Is it visible?
Yes, sir, it is visible. You can continue, sir.
Okay, thank you. So a warm good afternoon to all of you. The topic of my presentation is green nano composites for sustainable development. I'm Dr. Midun Dominic, currently working as assistant professor in the Department of Chemistry, Sacred Heart College, Autonomous, Tevara, Cochin. We are familiar with nanocomposites and nanoparticles, and we know that nanoparticles are those particles with size range between 1 to 100 nanometer. And there are several methods for the preparation of nanoparticles, like chemical methods are there, like salt gel method, solvochemical synthesis, high pressure homogenization, etc. So it's the era of green chemistry, and Paul Anastas, who is regarded as the father of green chemistry. And green chemistry is based on 12 principles. Among this, utilization of agricultural waste materials into value-added products is one of the important concepts of green chemistry. For example, we can prepare silver nanoparticles by the reduction method. For example, if we take silver nitrate solution, say 1 millimolar, and we may add sodium borohydride or lithium aluminum hydride as the reducing agent. This reducing agent reduces silver ions in silver nitrate into nano silver. So this is a chemical method for the synthesis or the preparation of nano silver. But here we make use of costly chemicals and some toxic agents, etc. So it's the era to treat or to prepare nanomaterials in a green way. So I will demonstrate a simple example by the preparation of zinc oxide nanoparticles. So zinc oxide nanoparticles can be chemically prepared by salt gel method, chemical precipitation method, etc. So here, this is a schematic diagram that well represents the preparation of zinc oxide nanoparticles from using the orange peel extract. Okay. So the first of all, the orange peel that is ground, dried and ground, and we powdered it, and it is treated with deionized water, and it is mixed with zinc nitrate solution. So the powdered extract is mixed with zinc nitrate solution, and we heat it at 150 degrees Celsius, followed by calcination at around 450 degrees Celsius. We may get zinc oxide nanoparticles. So this is a method that so this is a bioreduction method or bio method or green method for the preparation of nano zinc oxide. So we have used an orange peel extract for the preparation of zinc oxide. So the mechanism is illustrated like this. So this orange peel extract is a rich source of several flavonoids or carotenoids and lichenoids, etc. So they are represented as hydroxyl aromatic. They are having number of OH groups, and these hydroxyl compounds may form a complex with our precursor or starting material zinc nitride, and this is the compound formed, and we calcinate this particular complex, we may get zinc oxide nanoparticle. And we are all familiar with composites. Okay, composites are actually hybrid materials that comprises two phases. One is called matrix phase and a reinforcement phase. For example, if you consider natural rubber is having high tensile strength, but it is not conducting material. Its conductivity is less. But polyaniline is a conducting material. So if we prepare a natural rubber composite, natural rubber polyaniline composite, we may get the composite with excellent strength and excellent conductivity. So this composite consists of two phases. One is a matrix phase and the reinforcement phase. For example, here the matrix is having two different properties. It is having good shear properties and low density, and our filler or fiber, which acts as the reinforcing agent, which is having high strength, high stiffness, and low density. So if we mix these two, and we may get a composite, and this composite material is having both the properties of the fiber and the matrix. Composite is having high strength, high stiffness, good shear properties, and low density. So at this outset, I would like to talk on green tires. We are all familiar with rubber and its fillers used in rubber. Fillers are added into the polymer matrix to enhance its mechanical and thermal and barrier properties. Okay, so fillers can be broadly classified into two types. One is a black filler and a white filler. We know that carbon black is a black filler, whereas precipitated silica and nano clay, nano calcium carbonate, they are all examples of white fillers. So based on the reinforcing efficiency of a filler, fillers are again categorized into reinforcing fillers, semi-reinforcing fillers, and non-reinforcing fillers. Carbon black and precipitated silica are the commonly used fillers in rubber industry, and the properties of a filler mainly depends upon its particle size, particle shape, surface area, its structure, surface activity, and porosity. So moving on to the concept of green tires, why we need green tires. Okay, so as I said earlier, carbon black is the commonly used filler in rubber industry. Because of this, the tire of the car, which is black in color, we make use of 50 to 60 parts of carbon black in tire formulation. Even though this carbon black is having higher advantages, because carbon black is hydrophobic in nature, and our natural rubber is also hydrophobic in nature. So because of this hydrophobicity, there is good interaction between carbon black and natural rubber. So carbon black can be used as a common filler in tire industry. But this carbon black has got several disadvantages. It is produced by the incomplete combustion of petroleum-based products. So it is non-renewable. And the other one is, it is said to be group 2B carcinogen. It can cause cancer. And the other impact is that it has got several environmental impacts, and it provides some health hazards too. So scientists in the present era are trying to replace carbon black with novel biofillers derived from agro waste. And Michelin, who introduced the concept of green tires. Green tires means tires with low rolling resistance. The concept of green tires is not only using any bio-derived material in natural rubber, but if we make use of a material along with carbon black, there should be a reduction in rolling resistance. So rolling resistance is the friction or the energy produced when the when the car runs over the surface on the road. So lower the rolling resistance, higher will be the fuel saving efficiency, and lower will be the carbon dioxide emission from the passenger vehicles. So that is the concept of green tires. So green tires means tires with low rolling resistance that may provide a good fuel saving efficiency and less carbon emission from the passenger vehicles. And Michelin, and it is believed that if and there is a parameter that can determine this rolling resistance, that is tan delta. This can be obtained from dynamic mechanical analysis, okay, DMA studies. Okay, tan delta is called loss tangent. It is nothing but the ratio of loss modulus to storage modulus. So we have to remember one thing, that is tan delta at 60 degrees Celsius is a measure of rolling resistance. Lower the value of tan delta at 60 degrees Celsius, lower will be the rolling resistance, and higher will be the fuel saving efficiency, and lower will be the carbon emission. So this is the concept. We have to reduce the parameter tan delta at 60 degrees Celsius. Another parameter that is under our investigation is tan delta at 0 degrees Celsius. That is a parameter that determines wet grip, or when the passenger vehicle runs over the road, it do not squid. Okay. So higher the value of tan delta at 0 degrees Celsius, higher will be the wet grip, and lower the value of tan delta at 60 degrees Celsius, lower will be the rolling resistance. Okay, so this is a paper that we have published recently in Sustainable Materials and Technologies journal with impact factor 10. And here rice husk, we know that paddy cultivation is a part of the proud culture of Kerala state, and during milling of paddy, several million tons of rice husk can be obtained every year, and this rice husk is a rich source of silica. Okay, suppose if we burn rice husk at a very high temperature around 700 degrees Celsius for 2 hours, we may get this rice husk ash, and this rice husk ash is having 90% silica. Okay, rice husk ash is a rich source of silica. So we have collected 5 different varieties of rice husk, namely Jodi variety, Jaya variety, Kanjana, Uma, and Valichuri. And we found that rice husk ash that is obtained from Jodi variety, which is having higher surface area, around 79 meters square per gram. Okay, and we have incorporated this rice husk ash derived from the Jodi variety rice husk along with carbon black. We just replace 5 PHR or 5 grams of carbon black with 5 grams of rice husk ash. Okay, so NR neat means that represents without any filler, that is carbon black and rice husk ash. NRCB50 means natural rubber with carbon black 50 PHR parts per 100 or 50 grams of carbon black. And we replace 5 grams of carbon black with commercial silica. CS stands for commercial silica and RH stands for rice husk ash, 5 gram. So NRCB45 RH5 means 45 gram carbon black and 5 grams of rice husk ash. Okay, and we are surprised with the results because tan delta at 60 degrees Celsius, NRCB 45, commercial silica 5. So normally, according to the literature, carbon black along with commercial silica is used for the development of green tires. So here 0.15 is the value, tan delta at 0 degrees Celsius, but we could obtain the tan delta value decreases from 0.15 to 0.09. So lower the value of tan delta at 60 degrees Celsius, lower will be the rolling resistance and higher will be the fuel saving efficiency. So we could provide a provide a new formulation for the development of green tires by the synchronized use of carbon black and rice as cash. But even though the rolling resistance is decreased, we have got detrimental effect on the mechanical properties like tensile strength, tear strength, and abrasion resistance, etc. Because this rice as cash is having a low surface area around 79, whereas our commercial silica is having a surface area which is higher than that of rice as cash, around 200 to 300 meters square per gram. So by make use of commercial silica, we have got good mechanical properties, good abrasion resistance index, and rolling resistance too. So we are failed in improving the mechanical properties by the synchronized use of carbon black and rice as cash. But we could we were able to decrease tan delta at 60 degrees Celsius. So this is the concept of green tires. That is the graphical abstract of the work is illustrated here. So by the synchronized use of carbon black and rice as cash, we could obtain a less carbon emission and more mileage, fuel saving efficiency. So for a green tire, we have to, for any tire, not up to green tire, normal tire also, we have to concentrate on 3 parameters. That is called magic triangle of the tire. We have to consider wet grip, we have to consider abrasion resistance, and a rolling resistance too. So we thought the lower surface area of rice as cash may be one of the reasons for the detrimental effect of this rice as cash. So we would like to improve the surface area of rice as cash. How can we improve surface area of rice as cash? Or by preparing nanosilica. We thought it is better to prepare nanosilica. There are several methods available reported in the literature for the preparation of nanosilica, like a salt gel method. We can make use of TEOS or precipitation method using sulfuric acid in sodium silicate solution. So here we have adopted a green and simple method, one-step synthesis for the preparation of nanosilica by using Avera bilimbi fruit juice. In Malayalam, it is called pulli. I don't know what it is called in Kannada. So this is Avera bilimbi fruit. So instead of burning rice husk directly in a muffle furnace, first we treat this rice husk with Avera bilimbi fruit for 1 hour. And this Avera bilimbi fruit juice is washed away from rice husk. And then this Avera bilimbi treated rice husk is calcined in a muffle furnace at 500 degrees Celsius. At 6 hours, we will get pure nanosilica. So we are surprised with the results obtained because this Avera bilimbi fruit is a rich source of oxalic acid. So the oxalic acid content in the Avera bilimbi is enough to eliminate all the other metallic impurities that is present in rices like sodium, potassium, calcium. But in the literature, we could find that several scientists have used concentrated hydrochloric acid, sulfuric acid, nitric acid, and even aqua regia and piranha solution for removing metallic impurities from rice husk. So here we have adopted this rice husk and Avera bilimbi, that is a green method for the preparation of nanosilica, and this paper is under revision in Journal of Cleaner Production with impact factor 11. So we have prepare different composites. CS50 means commercial silica 50, and we have replaced 25 parts of commercial silica with 25 parts of BJRHS. BJRHS means bilimbi juice derived rice silica, treated rice silica, and BJRHS 50 means only BJRHS silica is there. So we have 3 composites. One is with commercial silica and 50-50 mixture of commercial silica and BJRHS and BJRHS 50. And we have to know the properties of the rubber composites. And look at the surface area. Commercial silica, which is having the surface area around 172 meters square per gram. But this BJRHS, the surface area is drastically improved from 74 or 70 to 1 ton. Rice cash is having a surface area of 70 to 1 ton, and this 1 ton to 204. So we could prepare a silica, nanosilica with excellent surface area that is greater than that of commercial silica and rice cash. And these are all the bet adsorption BJH plots and port size distribution. And this is the FTIR spectroscopy. FTIR spectroscopy is used to determine the functional group present in the material. And CS stands for commercial silica, RHA, BJRHS. So all these having similar peaks that represents the formation of nanosilica. And XRD analysis is also conducted. We could see that a broad peak at 2 theta is equal to 22 degree that confirms the formation of amorphous silica. So the blue one that represents BJRHS, and in the red one and black one, we could see that apart from the broad peak at 2 theta is equal to 22 degree, there are some shoulder peaks are there. So it might be due to some impurities, or it might be due to some crystallinity in the material. So a broad peak at 2 theta is equal to 22 degree in BJRHS confirms the formation of amorphous nanosilica. And this is the elemental analysis was conducted by the EDAX technique, energy dispersive X-ray spectroscopy. I'm not sure. I think the slide is somewhat blurred. Figure A, that is Rice's cache. Apart from silicon and oxygen, there are so many peaks, potassium, calcium, manganese, zinc, etc. is there. And commercial silica is also silicon and oxygen. Apart from silicon and oxygen, it is having aluminum and sodium, etc. But figure C, that is BJRHS, which is having only 2 peaks. One is for silicon and the other one is oxygen. So extremely pure nanosilica can be prepared by this treatment. And the SEM analysis was conducted and to know the particle size distribution and the surface, to know the shape and the surface morphology. All the samples are highly agglomerated because the silica is having number of silanol groups, OH groups on its surface. Because of the formation of hydrogen bonding between the silica particles, these silica particles are highly agglomerated. TEM image also shows agglomerated silica particles. So SEM and TEM is actually used to determine the particle size. And dynamic light scattering is also conducted to determine the particle size distribution. And the commercial silica, the particle size is around less 22, Rice's cache 35, and BJRHS 32 nanometers. So all the synthesized particles, all the prepared particles are in the nano regime. So we could obtain BJRHS, Rice's silica, with excellent purity and excellent surface area with lower particle size. So actually we thought, oh eureka, we have found a good material for replacing commercial silica in green tire formulation. But the results are when we go through the results, we could see that that is not the case. So regarding the cure characteristic, next we will discuss some of the important properties of rubber compounding. And optimum cure time, that is the time required for 90% vulcanization. So for cure time, that is for commercial silica, it will take around 7.98 minutes, and here it is for BJRHS, it is 6.62 minutes. So in the presence of BJRHS, or if you replace commercial silica with BJRHS, thus cure time can be decreased. So that is an energy saving. We can save energy. But what about the differential torque? Differential torque that determines the number of cross links formed during the vulcanization. But the cross links were significantly lesser. It is only 45, and here it is around 68. And look at the tensile strength and tear strength measurement. First, we thought we have prepared a nice material which is having excellent surface area and extreme purity and low particle size. But the results are, we are disappointed with the results, because look at the tensile strength results. It is for commercial silica 50. If you make use of 50 grams of commercial silica, the tensile strength is 9 MPa megapascal, but it is significantly decreased to 3 megapascal if we make use of BJRHS. So we were disappointed with the results. But what might be the reason for that? Even though the silica is having high, BJRHS is having excellent surface area, it is having high purity, low particle size, but results are, properties are decreasing. So tear strength is also decreases from 46 to 14. Okay, so what might be the mechanism? So we thought, during my PhD time, I spent almost 1.5 years to get a nanosilica BGRHS with high surface area. At that time, my aim was simply improving the surface area only. So I have taken different varieties of bilimbi, Avera bilimbi, and ripe bilimbi, and then we changed the reaction conditions, we changed the temperature conditions, we changed the treating time condition, we changed the calcination time conditions. Okay, and I have prepared around 25 samples and I've sent it for BET surface area, and I have I have optimized the specimen. But all the results were, but I was disappointed with the result. Okay, but then we formulate another mechanism in our paper, that is surface area is not only the single factor that determines the reinforcement effect of the filler. Along with surface area, we have to consider surface activity too. So in order to measure the silanol density, the number of OH groups on the surface of silica, we have conducted silicon NMR studies. From the silicon NMR studies, look at the geminal OH group values. The number of OH groups on commercial silica is 16, and for BJRHS is only 3. So that is a very crucial point in this study. That is, commercial silica is having high silanol density. Number of OH groups on commercial silica is very much higher than that of BJRHS. So normally, we make use of silane coupling agent. That is, TSPT is the silane coupling agent used in vulcanization, rubber formulation. And this is the actual mechanism involved. So we know that silica is hydrophilic in nature and natural rubber is hydrophobic in nature. So in order to improve the compatibility, in order to improve the interaction between the silica and natural rubber, we have to make use of a coupling agent. So TSPT is the commonly used coupling agent used in tire formulation, and T4SPT reacts with the silanol OH groups, OH and OC2H5. This ethanol molecule gets eliminated and the silica particles connected with the TSPT and the sulfur can be involved in cross-linking. So this is the method by which commercial silica can be connected to natural rubber. Whereas in the case of carbon black, the situation is different. Carbon black is hydrophobic in nature, so rubber is also hydrophobic, so there is no need for TSPT. In the case of commercial silica, we have to make use of a coupling agent like TSPT in order to provide good impact or good reinforcement. So, whereas our BJRHS, with the number of OH groups on its surface is less compared to commercial silica, so it cannot interact coupled with TSPT properly. So that might be the reason for the lesser mechanical properties. This is the proposed mechanism. So in the case of commercial silica and carbon black, carbon black is also having some COH functionalities and OH functionalities. Silica is having OH groups. So there is hydrogen bonding between the functionalities of silica and functionalities of carbon black. So there is network formation. This three-dimensional network formation will be possible between this carbon black and commercial silica or precipitated silica. And this three-dimensional network is responsible for transferring the stress. So because of this three-dimensional network, they are having higher mechanical properties. But this kind of network formation is not possible with BJRHS. So the same trend is also observed in the case of hardness and heat buildup, abrasion. Look at the abrasion resistance index value. So if you make use of commercial silica, this is having 120 abrasion resistance index, but it is only 56 for BJRHS. And this is regarding the thermogrammetric studies were used to conduct the thermal stability of the material. So the thermal stability is somewhat higher for BJRHS, that is T-on. T-on means temperature at which that is onset degradation temperature at which degradation starts. T50 means temperature at which 50% degradation takes place. And T-max means temperature at which maximum degradation takes place. So we could see that for commercial silica, the T-max is for 52 degrees Celsius, and here it is for 57 degrees Celsius with BJRHS. So higher T-max, higher thermal stability is for BJRHS composite. And this is all about the dynamic mechanical analysis, DMA results. And we could see that the glass transition temperature, TG, that could be obtained from the DMA, the glass transition temperature is not at all affected. There is only marginal change in the glass transition temperature. And look at the tan delta at 60 degrees Celsius. So commercial silica, 50, if we make use of CS50, tan delta at 60 degrees Celsius 0.05, but tan delta at 60 degrees Celsius for BJRHS is 0.03. So we could decrease, we were able to decrease the tan delta at 60 degrees Celsius, but we have to compromise other mechanical properties. And even though tan delta wet grip is greater, it is 0.14, but it is only 0.09. So this paper summarizes that we can make use of this BJRHS to decrease to decrease the lawn tangent at 60 degrees Celsius, to decrease the rolling resistance. But we have to compromise on the other mechanical properties. So we have to develop other strategy to synchronize with carbon black to lower tan delta at 60 degrees Celsius with excellent mechanical properties. We have, sorry, excuse me. How much of time I can take, sir?
You can take up to another 10 minutes is fine.
Hello?
Yeah, you can take for about 10 minutes.
10. Hello?
Yeah, can you hear me?
Okay, thank you. Okay, so this is also another work that our group has conducted with nanocellulose. And this paper is also published in Carbohydrate Polymers. And we have prepared nanocellulose from rice husk. We have prepared nanocellulose itself, nanocellulose by alkali treatment, bleaching, followed by oxalic acid hydrolysis. And nanocellulose were prepared from rice husk, and we mix nanocellulose with carbon black, and the same procedure that we applied. And here you have the result. NRCB30 tan delta at 60 degrees Celsius is 0.07. NRCB 15, NC 15 means nanocellulose. So if you replace 15 PHR or 15 grams of carbon black with 15 PHR of nanocellulose, tan delta at 60 degrees Celsius can be decreased from 0.07 to 0.04. So we can decrease the rolling resistance by the synchronized use of nanocellulose and carbon black. But the same trend we also obtained here. We have to compromise on other mechanical properties like tensile strength, tear strength, abrasion resistance index, and so on. Okay, so we have developed another material, that is nanocellulose, cellulose nanofibers from a common parasitic plant seen in Kerala, that is Cascuta reflexa. Cascuta reflexa, that is a parasitic plant. We have converted it into cellulose nanofiber, and we mix into NBR, nitrile butadiene rubber, and CNF. Composite is prepared, and we have got excellent properties. And again, chitin powder is prepared from shrimp shell waste, and chitin powder is prepared from shrimp shell waste, and this chitin powder is mixed with NBR latex. So this is polar in nature. NBR is polar. So we have got excellent reinforcement properties. And today I would like to talk on this particular paper, that is acetyl chitin. So a good news is that this paper is get accepted in Carbohydrate Polymers today. I have got the message today. So Carbohydrate Polymers. So this paper highlights the use of a chitin nanoviscous and the synergetic use of chitin nanoviscous and carbon black to improve all the mechanical properties as well as rolling resistances. We all know that chitin is the second most abundant biopolymer in the earth, okay, after cellulose, and it is actually having N-acetyl D-glucosamine units, and it is found in the exoskeleton of crab, mollusks, lobes, and shrimps. And this is the structure of chitin. And based on the arrangements of chitin, we have three different kinds of chitin: alpha chitin, beta chitin, and gamma chitin. And so this is the work summary. So from the two papers, we could understand that even though we were able to decrease the rolling resistance, we have to compromise on the mechanical properties. So our aim is it possible to develop a new material with excellent mechanical properties with low rolling resistance? So that we have prepared chitin powder from a prawn shell, and by alkali treatment followed by bleaching. And this chitin is acid hydrolyzed using oxalic acid and it is steam exploded, we may get chitin nanofibers. So this is the chitin nanofiber dispersion that we were prepared from prawn shell, and this chitin nanofiber is first dispersed in natural rubber latex. So in the other two cases, in the case of silica, we are directly adding carbon black and silica in a 2-roll mill. Here the situation is different. At first, we have got a uniform or highly dispersed chitin nanofiber in NR latex, and which is oven dried. We make a sheet, and it is mixed with carbon black in a 2-roll mill, and we analyze the properties. And so this is the preparations chart. So we have prawn shell. It is alkali treated, followed by bleached, acid hydrolyzed. We may get chitin nanofiber dispersion. And these are the characterization techniques. We could get, there are two peaks at 1654 and 1618 centimeter inverse that shows alpha chitin is present in our sample. C13 NMR also shows alpha chitin is present in the sample. XRD is also used to, or it affirms the formation of alpha chitin, and the crystallinity index can be calculated from the X-ray data, and crystallinity index of chitin nanofiber is around 90% crystallinity index. So our prepared material which is having high crystallinity index, and this is TG car, and the thermal stability is very high, around T50 is around 340 degrees Celsius. And these are the 10 image. So this is the beautifully arranged network fibers that shows chitin nanofibers, and the surface area is calculated from the BT analysis. It is around 2 meters square per gram. So we have formulated different mixes: mix 1, mix 2, mix 3, mix 4. That is, we just change the way we just sorry. We just change the composition of chitin nanofibers from 0.1 pHr to 5 pHr. Okay, and we make a carbon black composition as fixed. Carbon black is fifth, so carbon black is 50 plus 0.1 chitin nanofiber. Carbon black 50 and 5 pHr of chitin nanofiber. And look at the results. Look at the tensile strength results. So mix 1, which is having not carbon black and chitin nanofiber, the tensile strength is 16 megapascal. And for with carbon black alone, CB50 alone, tensile strength is 21. And if we make use of carbon black 50 and 1.5 grams of chitin nanofiber, tensile strength improved from 21 to 24. Wow, we have succeeded to. In the previous examples, tensile strength was decreased. Here, tensile strength is increased from 21 to 24. Tear strength improved from 89 to 110. And abrasion resistance index, which is also improved from 106 to 115. So we could obtain excellent mechanical properties by the synchronized use of carbon black and chitin nanofiber. And this paper is accepted in carbohydrate polymers. And swelling index, that is, we have conducted the swelling characteristics in toluene. Here it is a 187 and here it is a 185. That is, swelling index is decreased and cross-link density is improved from 9.07 to 9.36. And we have proposed a mechanism. This might be the mechanism. So this is a figure A, which is having carbon black alone. So the grape like things which is represented, that's the carbon black. So we have carbon black, and we have carbon black and chitin nanofiber. This black color will be chitin nanofiber. So in the first example, this solvent molecule can easily penetrate through the sample. But so here in figure B, these solvent molecules may pass through a tortuous path. It may follow a tortuous path, so more time is needed. That is why swelling index decreases. And this carbon black and chitin nanofiber, the carbon black has got several functionalities, and chitin nanofiber is having several functionalities. So there is intermolecular hydrogen bonding possible. So network formation will be there, and the 3-dimensional network formation that is responsible for the improvement in the mechanical properties. And regarding the thermal stability, there is not that much change in the thermal stability. That is almost 404, 403, 404. So thermal stability is almost constant. And regarding the fructographic studies, we could see that no fiber pull out are seen, but at a high pHr, 5 pHr, there are voids will be there. So that might be the reason for lower tensile strength at high pHr loading. And look at this tan delta values from the DMA analysis. So tan delta at 60 degrees Celsius, that is a parameter that determines rolling resistance. And here, look at carbon. If we make use of carbon black 50, it is 0.14. But if we make use of carbon black 50 along with 1.5 pHr of chitin nanofibers, the tan delta at 60 degrees Celsius decreased from 0.14 to 0.07. Okay, 0.14 to 0.07. So about 50% decrease. About 50% decrease in tan delta at 60 degrees Celsius can be obtained by the synchronized use of carbon black and chitin nanofiber with not compromising the mechanical properties. So these are all the graphs. Okay, so I think I don't have much time to discuss the second part of my lecture, because I have also prepared some slides on the PVA, polyvinyl alcohol, on sustainability, sustainable packaging material, but we don't have enough time to discuss all this. So I just stop my lecture here. So thank you so much. Thank you for giving me an opportunity to deliver a lecture on green tires. Thank you, sir. Thank you so much.
Thank you, sir. Thank you, sir.
Okay.
So, for the participants, we have shared the feedback link. So, we have come to the verge of closing this one-day national webinar. Now, I would like to request Dr. C.S. Onnegowda, Head of Department of English, JSS College, Nanjangud, to present the vote of thanks.
Last, thank you.
Yes, sir.
Good afternoon to all of you.
ಬೇರೆ ಡಿವೈಸ್ ನ ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಳಕ್ಕೆ ಹೇಳಿ ಸರ್ ಅಷ್ಟೇ.
Am I audible?
Yes, sir.
Okay. Now, it gives me an immense pleasure to propose the vote of thanks on this occasion. At first, I would like to thank Professor S.M. Shivprasad, Director, Higher Education Council, and Professor JNC ASR Bangalore for his wonderful keynote address. He has enlightened the gathering to go up to their estimation in future days. Thank you very much, sir. And also, I would like to thank Professor K.N. Loknath, Director, PME Board, University of Mysuru, for his very suggestive presidential remarks delivered by him. Thank you, sir. And Professor C.V. Ellamagad, Senior Scientist, CENS Bangalore. As a resource person, he has tried his level best to convince all the participant scholars to make their future better with regard to their subject teaching. Thank you very much, sir. And one more resource person, I would like to extend my hearty thanks to him, Professor Mithun Dominic, Sacred Heart College, Kochi from Kerala State, and who really has enlightened the gathering to learn yet more knowledge from all possible ways. Thank you very much, sir. And it is my privilege to thank our beloved professor, Professor H.S. Nagendra Kumar, who has been with us in all the respect to make such a programs more meaningful and convenient in all the respectable possibilities. And I would like to thank our beloved principal on behalf of our college. And at the same time, it is my wish to thank my colleague, dear friend, and the IQAC coordinator of our college, Dr. B.K. Kendagan Swami, and who has been putting more effort to make these kinds of the programs more meaningful day by day. Thank you very much, sir. And also, I would like to thank our senior faculty members, Madam Sridevi, and who has been our backbone support in making these kinds of the programs, even in the interest of the students as well as the interest of the teaching community. And thank you, madam, and Deepali madam, and Sri Ravitej. These two have been working in our college as the assistant professors in the Department of Computer Science and in the Department of Physics, and who have lent their intellectual support as moderators. And I extend my heartfelt thanks to these two persons. Thank you, Madam and Sir. And it is my sincere interest to extend my or to convey my heartfelt thanks to my dear young friend Mr. Ullas, and who has been lending his full support in making almost all kinds of the online programs to be enlightened and to be broad to make it more sensible and very meaningful. And I convey my special thanks to my dear friend Mr. Ullas Ji. Thank you, sir. And also, I would like to thank all the participant scholars of our college and the participant scholars from the different colleges, the
Sir, we have lost you, sir. Okay, I think there might be a small technical error or network issue. Just give us a second. Okay, so there is a small technical issue. Okay, so we have come to the verge of closing today. So I would like to thank everyone for your patient listening, and also I would like to thank all the presenters and the speakers who have given such a wonderful knowledge for all of us. We all have got the ability to look at the things in a very new perspective now. So thank you so much, all the speakers. I should definitely thank Professor Dominic here. Thank you so much for your time. We would like to hear you from you about the other topics that you have prepared for maybe in the upcoming sessions. Thank you so much, sir. So thanks, everyone. Yeah, thank you, sir. So thank you.
Thank you, sir.
Your feedback link has been already shared in the chat of YouTube link, and also will be shared in the WhatsApp group. So with that, you people can fill in the feedback later with respect to your presence, and also the feedback. Your e-certificates will be sent on an email, maybe in a couple of days. Okay. Thank you so much for all your presence. We look forward to meet you all again. Thank you. Thanks, everyone. Bye-bye.
Thank you.